So, good morning, good morning, and welcome you back to our 2 days national webinar on recent advances in mathematical sciences. So, today our first speaker is Dr. Anita Pal. She is Associate Professor, Department of Mathematics, National Institute of Technology, Durgapur in West Bengal. She is involved in teaching and research for more than 12 years. She has more than 110 publications in reputed national and international journals and 21 conference papers. Many of her publications are in many SCI and Scopus Index journals. A good number of students are working her supervision, and Dr. Pal has successfully guided 10 research scholars for PhD degrees and 21 MTech and MSc project theses. Her specialization includes algorithmic graph theory, fuzzy mathematics, and operation research. Dr. Pal is the author of the textbook Engineering Mathematics Volume 1 and Volume 2, and a book chapter of rough set, fuzzy set, and soft computing published by Narosa Publishing House, New Delhi. He organized more than 15 national and international conferences, seminars, and workshops. Till date, she has attended 43 national international conferences, workshops, and seminars in India and abroad also. She has visited China, USA, London, Singapore, many countries to deliver invited talks and chair the sessions. She is a member of some professional bodies like ADMA, Indian Mathematical Society, Indian Society for Technical Education, Advanced Discrete Mathematics and Application, etc. She has successfully completed two research projects by DST New Delhi, and one high budget project is undergoing. She is member of editorial boards of many journals like International Journal of Computer and Information Technology, Annals and Pure Applied Mathematics, etc. She is also reviewer of many reputed journals. Has good collaboration with some industries. So now I request ma'am to start her invited talk. Actually, sorry for the interruption. Ma'am, we are getting disconnected with Anita ma'am. Okay, ma'am.
So yes, now I can hear you. I can hear you.
Okay. And we can see you.
Okay.
Now, please start your invited talk, ma'am.
Okay. Thank you so much. Thank you. So at first, I would like to thank Shantal Ved Roha Sarda Shotabarshuki Mahavidyalaya, Department of Mathematics. It's in Goaltore, Paschim Medinipur. Thank you for giving me the opportunity to talk. And I'm really happy that in this pandemic situation, you people are organizing this 2 days national webinar on recent advances in mathematical sciences. So let me start my presentation. I can see Mukti Acharya madam. Madam, how are you? It's nice seeing you after a long time. Madam, your microphone is mute. Please unmute yourself. You're saying something. How are you, madam?
I'm keeping fine.
That's great.
Everything
You are looking fine. You're looking fine.
Thank you. I make myself active so that I can join you people.
Very nice of you. Okay, ma'am, let me start my presentation.
Surely. Most welcome.
Okay. Can you see my slide?
No, ma'am.
Oh, you cannot see my slide?
No.
Okay. Okay, just a minute. Now you can see?
Yeah, ma'am.
Oh, that's good. Okay. Today I'm going to talk about application of minimum spanning tree in water supply management. So as Dr. Nasrin Khan has already introduced me, Pal, Department of Mathematics, NIT Durgapur. Now see, all of us, we know that water is very important. It's a very important thing. Without it, we cannot think about our life. So every day it is our habit that in the morning, if we put on our taps, if water is not coming, we will panic. So water is life. So without water, life cannot happen. So how we are getting this water? We are getting this water through some pipelines from some resources. It's being supplied to our houses. Now this pipelines which are laid to our houses, that is actually a network. So this network we can compare with graph. We can think it or we can connect it, we can model it in a graph. So today I'll be talking about a little bit like that. That water supply network is a water distribution system created by people. Obviously, people only creating this. And water supply system is in the order usually consist of water intake structures, water treatment structures, water supply, pumping stations, adjustment structures, drainage pipes, water supply pipe network. And based on actually our actual demands to solve the economic problems of water supply network, what we want to ensure the lowest cost in laying the pipelines. Everybody of us, we know that water is very important. We want water in our houses. Everybody, let it be poor, let it be rich. Every person, every individual needs water, and that water should be supplied to their respective residents. For that, we need to lay pipelines, and obviously, we need to check the cost factor. We will always try to do or model the whole pipeline system in such a way that it should meet the requirement of people, and it should also, the cost incurred should also be minimum. So both the things we keep in our mind when we are actually modeling this water pipeline network. Now actually we establish a mathematical model of water supply network, and we use graph theory to solve such problems. The minimum spanning tree is used to establish to ensure the costs are lowest in the case of this pipeline connectivity. We know that those who have learned graph theory, they know that there are algorithms to find the minimum spanning tree, Prim's algorithm, Kruskal's algorithm. So today I will discuss one of the algorithm. I'll pick up Kruskal's algorithm. I'll make you understand that how this Kruskal algorithm works. So using Kruskal's algorithm to generate the minimum spanning tree, we actually have taken example also, and I'll show you that how it is working and how we are getting the minimum spanning tree using Kruskal's algorithm. Now, most of our classical methods for formal modeling and computing of those optimization problems are crisp, deterministic, and precise in character. Now, see in my picture, you can see that one central office I have taken. If you see the left hand side, one central office is there, and many houses are built. And in the next right hand side diagram, you can see that some pipelines are laid to the houses. That is mean from the central office, some pipelines are given to all the houses. Now see, we can do like this. Central office, as many houses are there, you can directly give pipelines or provide pipelines. So every house will get the water in adequate amount. Go with such a network or such a modeling, it will be very expensive, because here we have not tried to optimize it. From the central office, directly we have given the pipelines to each and every individual house, which is not a good technique because it will be very expensive. So we would definitely have two objectives when we are laying the pipelines. One objective is that everybody should get water. Second objective is that we should minimize the cost of laying these pipelines. Now see, if you go with this diagram, this is much better, because central office is giving the water to every house, but it is not giving directly. We have tried to minimize it. Before coming to spanning tree, let me just tell you what is tree. Those who are very new to graph theory, for them, I would just like to define what is tree. A tree is a graph without any cycle and it should be connected. Graphs can be connected, graphs can be disconnected. So a graph can have many cycles, graph which should be connected and which should be without any cycle. We call it acyclic. Any graph which is without any cycle, we name it as acyclic or cycle free. So tree is a connected acyclic graph. Whenever you have two or more trees, we name it as forest. Just in normal life or in natural life, what we say, like when we see many trees together, we say this is a forest. Even in graph theory, two or more trees together form a forest. Forest is a cyclic graph. Now here I have taken some examples, very simple examples. One tree is with one vertex. Then you can see tree with two vertices, tree with three vertices, tree with four vertices. So on you can draw. So when I'm drawing the tree, what I'm keeping in mind, one is they should be connected and another is there should not be any cycle. Now what I mean by this spanning tree. Now first let me tell you what is a spanning subgraph. Suppose you are having a graph G which we generally denote by VE, set of vertices, set of edges. Now this spanning subgraph G dash is V dash E dash, where this V dash will always be equal to V and E dash will be actually subset of E. Here it is just in opposite way it is written as spanning subgraph of G is a subgraph with vertex set V if G dash V dash E dash is a spanning subgraph of G if V equals to V dash E is subset of E dash. That does mean what? The same, whatever the graph will have as many vertices, your subgraph will have that many vertices and S set will be the subset of the S set of your graph, the graph which you have taken to draw a spanning subgraph. A spanning tree is a spanning subgraph that is a tree. That is mean it should be a spanning subgraph and it should also satisfy what is the definition of a tree? Tree should be connected in tree. Now next we come to minimum spanning tree. So first I say what is tree. I have shown you X, two vertices, three vertices. Explain what is spanning tree. Right now I'm going to talk about what is minimum spanning tree. Now see, whenever we are studying a graph and if on the edges nothing is given, no weights are given, no numbers are assigned, we say it is a non-weighted graph, or we say that, or we take it as 1. Okay, we take every edge weight is 1. But in some problems, we need to have the weights. What the weights actually signify? The weights signify many things. Suppose it is a road connectivity, then you can say the edges will maybe it's in kilometer the distance is given, or you can say it may be price, it may be time of traveling. So the weights can be anything. So as per our problem, we put or assign some weights of the graph. It is not always necessary. You can have unweighted graph and you can have your own problem. But sometimes for our problem, we need to have some weights which signifies many things like cost, like time, like distance, and so on. So when we talk about minimum spanning tree, we generally talk about weighted graph, where we assume or we take that some weights will be non-negative weights will be assigned to each of the edge. And this minimum spanning tree is that we are going to make or find out such a spanning tree whose weight will be minimum. That does mean since all the edges have been given some weights, you are going to add them up. After finding the spanning tree, you are going to add the weights on all the edges. Whichever spanning tree is going to give you minimum weight, that will be your minimum spanning tree. We also call it minimal spanning tree, or minimum cost spanning tree, or sometimes also referred as shortest spanning tree. One thing I should say that a graph is not having only one spanning tree. Graph can have many spanning trees. It's not a unique representation. So here by minimum spanning tree, we mean to say that the cost incurred will be minimum, or the weight will be minimum. Now see here, I have taken example. A spanning tree of G is a subgraph T that is connected acyclic, includes all the vertices. You can see I have taken a graph and one bold line you can see. So these bold lines, why I have taken? Maybe the weights were minimum. I have tried to find a spanning tree, keeping in mind that my spanning tree should contain all the vertices and my spanning tree should be minimum. Now see, here I have taken an example, an undirected graph G with positive edge widths. What is our aim? Our aim is to find the minimum weight spanning tree. You can see all the edges have been assigned some weights, 4, 6, 16, 24, 23, 18, like that. As anything, like you can say that from one vertex to another vertex, if you want to travel, all the vertices you can take it as a city. If you want to travel from one city to another city, maybe these are the distances. Okay, or this may be the price of the bus fare. Okay, something like that. So these ways can have your problem as you're defining your problem. So here one weighted graph I have considered. All the edges have been given some weights. You can see the weights 4, 6, 16, all these weights we have given on every edge. Our aim is to find a spanning tree whose weight will be minimum. Now see, for this particular graph, I found this minimum spanning tree. And how I'm calculating the weights, you can see the bold lines and the weights, all the weights I have taken, those were on the bold lines, that the edges, that is 4 plus 6 plus 8 plus 5 plus 11 plus 9 plus 7. Okay, all these weights I have added up and it gave me cost 20. The weight of this spanning tree is 50. So for this particular graph, the minimum weight or the minimum spanning tree cost 50 or weighs 50. Now see, this is actually a model of nature only. You can see sometimes we come across such type of thing, no? In a plant or the tree, you can see structure like this. So we can think it like a minimum spanning tree of a random graph. We can think in this manner. Now there's lots of application of MST. It is used in cluster analysis, real-time face verification, codes for error correction. It also helps in finding road networks in satellite, aerial imagery, approximation algorithms for NP-hard problems, network design, and many other applications are there. Now, as I said, minimum spanning tree can be obtained using many algorithms. There are many algorithms to find out minimum spanning tree on a graph. Very popular one, two are very popular. One is Prim's algorithm, another is Kruskal's algorithm. Very basic and very popular. So it's not possible to discuss both the algorithms, but I will try to make you understand how Kruskal algorithm works. See here, I have taken the graph G. The vertex set P contains V1, V2, Vn, and the edge set contains E1, E2, En. And it is obviously a weighted graph. If G has any self loop, please delete it. Whenever you are applying Kruskal's algorithm, look into your graph. See if your graph is having any self loop. You cannot take care of that. It is not required to have that. So just delete it. If there are many ages, we call it multiple ages, keep only the age whose weight will be minimum and delete all other multiple ages. Then arrange all the ages according to the increasing order of their weights. Next, what we do, we select the age with least weight and add it to the subgraph. Next step, we select an age whose weight is second minimum, and then again we add it to the age to t. Similarly, we go for the next one, till what we will go? As many vertices are there. So, if tree T is having n vertices, we know it's going to have n minus 1 edges. So, we'll go for, when we are going for a spanning tree, we go till all the vertices are touched. Now, see, this is the Kruskal algorithm. What I'm giving input? I'm giving a simple, connected, weighted graph G. What is a simple graph? Simple graph is a graph without any self-loop and parallel edges. So I'm giving input because I said in Kruskal algorithm, if you are applying Kruskal algorithm, if your graph is having any self-loop or multiple edges, you need to delete them. If self-loop is there, just delete it. If multiple edges are there, take the edge with minimum weight. Remaining edges, please delete from the graph. So in input, what we are giving? We are giving a simple connected weighted graph G. In output, what we are obtaining? We are obtaining a minimum weight spanning tree T. So only two steps are there in this algorithm. Arrange all the edges according to the ascending order of their weights and least L. In step 2, what we are doing? Initially, we are taking T as empty, running a while loop. T has less than n minus 1 edges. Choose an edge UP from the list where you have kept all the edges with their weights. If UV does not form a circuit in T, add that UV to T, select UV. So this is how the while loop will run and Kruskal ends. The algorithm is like this. Now I have taken an example to make you understand. See, in my example, I have taken a graph. My graph is having 5 vertices, V1, V2, V3, V4, V5. And you can see all the edges have been assigned some weights. V1 to V2 is 2, V1 to V4 is 5, V2 to V4 is 3, and so on. Just now I explained Kruskal algorithm. What we are going to do? At first, we are going to write the age weights in ascending order. No? See, first I have written just copied the weights. V1, V2, 2, V1, V4, 5, V1, V5, 5, V2, V3, 6. Just I have copied the ages and the weights. Next, what I did? The sorted list of edges according to the increasing weights. Now I have sorted it and I have written it in this manner. 1, 2, 2, 2, 3, 4, 5, 5, 6. So I have arranged it. I have sorted it. So this is what you have to do in your first step. Second is what? You have to start your making your minimum spanning tree. You need to draw your minimum spanning tree. How you will start? You will start with that particular age which is giving you minimum weight. So I'm going to start my tree with V4, V5. See, I have started with V4, V5 because its weight was only 1. Next what? Next was 2. V3, V5 I can take, V3, V4 I can take, V1, V2 I can take. Any one as per your wish you can take. Only check it should not form any circuit. Okay, only check is it should not form a circuit because we know that tree is acyclic, tree is circuit free. So if you are adding any edge and it is making a cycle, then you cannot add that. Next what I did, I have taken V4, V5, V5, V3. Now my first figure was tree with 1 edge, that weight was minimum. Then I have taken tree with 2 edges, now tree with 3 edges. Choose the edges in this manner of minimum weight. Keep on adding to the tree. Now see, the tree is almost done because V1, V2, V3, V4, V5, all the vertices are there in my tree. So this tree has 4 edges. The graph contains 5 vertices. Therefore, no more edges are required for the spanning tree T. So we terminate the process. And the weight of this spanning tree is sum of the weights of the edges in T, and that is 1 plus 2 plus 2 plus 3 equals to 8. I hope you understood that how I made my spanning tree. Now, an application of MST in water supply network. This water supply network is a water distribution system created by people, as I say. Here, actually, we are laying the pipelines in this manner only. As I have shown you the MST, it is in the same manner it is modeled, where we keep in mind that we are going to take or we are going to lie the pipelines in such a manner that it should not cost you too high. And the every house should get the water with objective paying minimum amount. And this minimum amount assurance is giving from our MST algorithm. This is one algorithm I have shown you. Another algorithm is also there. Many other algorithms are there. So if you are interested in graph theory, if you want to work with it, so you can easily go with the algorithms. You can learn yourself. These algorithms are very useful. So this MST actually we can model in this water supply management. Now see here I have taken an example. Suppose Mere House is there, brewery is there, bakery is there, okay, there Thomas Farm is there, dry cleaner is there. So many houses, or you can say that needs are there. Everybody wants water. So using our MST, and we suppose know that if you want to go from Mayor's house to bakery, if you want to lay the pipe, it is going to, the distance is 10 meter. Okay. So all the, you can say all the distances are given. Obviously the scale is not maintained over here. Use our MST technique. If you draw the MST, if we consider all the houses as vertices, and if we consider all the pipelines as the edges, then it is nothing but a graph. And if we apply our algorithm, we will definitely get the minimum spanning tree. And for this particular problem, the weight of the spanning tree here is 79. Now see, the water supply center and users in the planning area are referred to as nodes. As just now I said that you can take all the houses, all the required points as graphs and the pipelines as edges, and cost of laying or the distance, whatever given as weights, you can consider them as weights. Weights should be positive. So the routes that may be lying between the nodes intersections can be considered the edges, as I said, and the sum of construction cost and operating cost of each line is regarded as the weights of the edges. And sum of weights is the minimum, that is the lowest cost. That is the purpose of design we want to achieve. We want to achieve two things. Our motto was to, one, that everybody should get water and pay minimum amount. So this is how we actually modeled our problem. Now see here actually what we have done. We have taken the weights as very crisp numbers. Many people right now, they are working with fuzzy. You can take these as fuzzy numbers also. You can use fuzzy theory also in MST. Fuzzy minimum spanning tree is also there. I myself, I have worked. We have lots many paper in fuzzy minimum spanning tree where the weights have been taken as fuzzy for the fuzzy operations. So you people can also go with those papers, and they're very practical also, because sometimes it happens that you cannot exactly say about the weights. You exactly don't know. So we can take interval numbers. We can take fuzzy numbers that will give you better result, or it will be more applicable. So fuzzy spanning tree is also there. So if you are interested, I can share some of my papers with you all. So in future, we will study our introduce algorithm approach in real life scenarios, like even in transportation, we can take wireless communication network, and many other optimization problems can be modeled using this chemistry problem. and we can also improve the complexity of the proposed algorithm. So these are some references. Sorry, sorry, I have written future work. Sorry, these are my references. Thank you. Thanks a lot for patient hearing.
Ma'am, thank you very much for sharing with us such a nice presentation. Actually, you have taught it us in a very simple manner or in a very simple way. I think this is for the new researcher and the students. They will be very benefited from your speech. Thank you very much.
Thank you. Thank you.
And actually, I have one question. The water management supply, any problem can be solved by operation research also.
Sure.
So can we solve it by using both methods?
Yes, obviously you can solve with both the methods because traveling salesman problems are there. People are not simultaneously. Both are different approaches. Both have different approach. Here our approach is very different. No, we are modeling in a graph. Operation research doesn't model in a graph. They take the problem in a different manner. So you have to pose your problem in a different manner when you are going to use those techniques of operations research. Then you have to model your problem in that manner. We graph theorists, we always try to model the problem into a graph. We always try to find out a structure which resemble our graph, and we try to put all the techniques which we know to solve the problem.
Okay, thank you. So Mukti ma'am is here, and our Dr. Ash Sundaresaran also here. So ma'am, have you any question?
No, from my side there's no question.
Okay.
Because I have heard regarding her fuzzy minimum tree also.
Yes.
You gave a talk during ADMA conference.
Right.
It was held at Tumkur, if I remember.
Yes, madam. It was in Tumkur only, right? My God, you have a very good memory. I must say, you have a very good memory. Yes, in Tumkur, I said about fuzzy minimum tree.
This is just now I'm working after my MSc. I'm working in graph theory, but basically I'm a person of OR.
Okay.
My MSc was in OR, but after coming to Allahabad, then when I started talking about OR, Dr. Acharya, who later on became my husband, said, "What are you doing? Are you doing all your methods, that method, that method? You are drawing graphs only. You are doing graph theory. So you come to graph theory." So like that, I entered into graph theory, but I love to read some books in OR and all other things because I'm not very much familiar in books in OR written by Indian authors. Okay.
So sir attracted you using graph theory. So I must say that sir attracted you using graph theory.
First we were just friends, then we got acquaintance, then we got permanent acquaintance.
That is great. That is great.
I'm very much thankful for your lecture, for the beginners and people who are learning graph theory, making them just some basic concepts. But here a lot of concepts like graph, then tree, then spanning tree, all those concepts has been taken care by you through the examples. So it was a nice lecture. I liked it.
Thank you, madam.
Thank you very much.
Always keep on blessing us like this.
Oh, I'll see. My blessings are always with my youngers, but I ask my elders to send your blessings to me.
You are always fit and fine, always doing well.
Thank you.
Always very, very much involved.
Thank you.
We try to be like you.
Thank you.
We don't know whether we can be like you at your age, the way you are active.
Anita, I'm free from all other work. No work, no bother about kids, no grandkids. So you take care of your family. So I will take care of myself.
That's very good. Okay. Very inspiring, ma'am. You are very inspiring for us. We would like to be like you. At your age, you are doing so much of research.
You people are much younger to me.
Thank you, madam. Thank you so much.
Okay, thank you. Thank you. Thank you. Yes.
Thank you.
Sundaresan sir also here. Sir, sir, can you hear me? Dr. R. Sundaresan?
Yeah, we can see him, but he's muted.
Yeah. Okay, thank you, ma'am, once again.
Thank you so much. Thank you.
So we'll get in touch.
Sure. So I can leave because we have admission test today. So we have to get inside. Okay, thank you so much.
Okay. Welcome.
Thank you, madam. Thank you, all the participants. Thank you, Nasreen. Thank you, your Department of Mathematics, all the faculties, those who have taken the main program. Thanks a lot to everybody. Thank you. Thank you so much.
So we will be coming back few minutes later to our next speaker.
Good morning, Nasreen.
Okay, good morning. So we are having our next speaker.
Can you hear me?
Of course, we can hear you. Can you hear me?
What happened? I cannot hear you. Hello.
Yeah, we can hear you, sir. So keep your microphone
Hello.
on,
Hello.
please. Yeah, we can hear you, sir.
Something wrong here. Okay.
So
Just
please rejoin.
Can you hear me, Nasreen? Okay. But I can't hear you.
Can you hear us?
No, what's the problem?
So keep your microphone
Okay, I'm
on,
leaving
sir.
and rejoining.
Okay,
And so
okay.
let's see what happens. So I have joined again, Nasreen.
Can you hear us?
Yes, yes,
Sir?
yes. Now it's
Okay,
okay.
okay.
Now it's
Okay,
okay.
thank you.
Okay.
Now we are with us, our next speaker, and I request Mrs. Maitri De to introduce him. Maitri, please.
Our next speaker, Dr. Sheikh Mohammad Abu Noim, Associate Professor, Department of Mathematics and Statistics, Alia University, West Bengal. Dr. Naim did his MSc and PhD from Vidyasagar University in 2001 and 2007, respectively. He joined Jhargram Raj College as assistant professor in 2000. Then he joined Alia University in 2010. His research interests include algebraic and algorithmic graph theory. He has more than 30 research articles in international journals. He is the reviewer of journals like Arts, Combinatorial, Discrete Mathematics, Algorithm and Application, Polycyclic, Aromatic Compound, Journal of Combinatorial Mathematics and Combinatorial Computing. Under his guidance, many research scholars are doing their postdoctoral course. Now, sir, please start your invited talk. Thank you.
So I thank you, Maitri, for introducing me. And I
Thank
thank the
you, sir.
organizer, especially Nasreen and all other organizers and the college authority for giving me this opportunity to share some thought about some recent advances in mathematical sciences. During this pandemic, when life has been stalled in every sphere, the only good thing what we have, I think, is that these webinars, where we can participate from the ease of our home without thinking of any logistic or any travel. We can participate in many number of such conferences and webinars through virtual presence. So I thank you once again for giving me this opportunity. Now I'm going to uh, present my screen. Is it visible?
Yes, yes. Visible.
Okay. So I'll be talking on Laplacian eigenvalues and Kirchhoff index of some graphs. As you have already heard some lectures on graph theory, so I think we need not introduce what a graph is and what are the ways to represent a graph. One such way of representing a graph is adjacency matrix. You know, the adjacency matrix is a square matrix. If there are n vertices in the graph, then it will be an n by n matrix where the elements will be either 0 or 1. If two vertices are adjacent to each other, then their corresponding element will be 1. And if they are not adjacent, that is, if two vertices vi, vj are not in the edge set E, then their corresponding element in the adjacency matrix will be 0. It's very familiar to us. Now, a new kind of matrix called the Laplacian matrix is also being studied by the graph theorists so much. And it is defined as the difference between the degree matrix and the adjacency matrix. What is the degree matrix? Whose diagonal entries are the degrees of the vertices of the graph. And if we take the difference between the degree matrix and the adjacency matrix, then it will be the Laplacian matrix. Let's give me an example. This is our graph G. Then you know the adjacency matrix is given by here a 4 by 4 matrix. 1 is not adjacent to 1, so it is 0. Adjacent to 2, adjacent to 3, adjacent to 4, all. 2 is adjacent to 1, not adjacent to 2 itself, but adjacent to 4, not adjacent to 3 also. 3 is adjacent to 1 and 4, not adjacent to 2 and 3 itself. And 4 is adjacent to 1, 2, 3, all. Now, if I take the diagonal elements as the degrees of the corresponding vertices, here the degree of the vertex 1 is 3, degree of the vertex 2 is 2, that is 2 for 3 also, and 3 for 4. And these will be -1, -1, -1, -1, 0, -1, -1, 0, -1, -1, -1, -1. This matrix will be the Laplacian matrix of the graph G. As we see that the Laplacian matrix can be easily derived from the adjacency matrix itself, because in the diagonals, there's a degree. Degree means the number of ones present in the corresponding row. So the Laplacian matrix and adjacency matrix necessarily have the same information, carries the same information, but the Laplacian matrix is somehow more useful relating to its spectrum. That, like the adjacency matrix, the Laplacian matrix is also real and symmetric. We have changed the diagonals. In adjacency matrix, the diagonal elements were 0. In Laplacian, diagonal elements of the degrees, and the corresponding elements of the adjacency matrix has become -1, still symmetric. As it is a real symmetric matrix, all its eigenvalues will be real. Now, why this matrix is out of nothing called Laplacian matrix? As we know, in adjacency matrix, it carries the information about the adjacency of the vertices. In incidence matrix, it carries about the incidence relation between the vertices and edges of the graph. But why this matrix is called a Laplacian matrix? Because it has some resemblance with the Laplacian operator. Suppose we are considering heat distribution across an infinite graph. It's an infinite graph. It says at some particular vertex I, suppose the heat is phi I, and at some vertex j, it is phi j. Then the difference of heat or the difference of temperature between these two vertices is phi I minus phi j. So by Newton's law of cooling, the change of rate of change of heat will be directly proportional to the difference between the heat at the adjacent vertices. So if you take all the differences, then we have to take the sum over all j, which are adjacent to the vertex I. Now, to 1 to n, because which vertices are not adjacent to I, for them aij is 0. So the sum will remain same, and minus k has come due to some heat capacity k. Now if we expand the sum, then phi I can be taken out of the sum j. So it is phi I sum over j aij, and the second term will remain as it is. Now we know sum over j aij is the degree of the vertex I. That is how many vertices are adjacent to the vertex I. That's the degree of the vertex I. So we are getting phi I di minus sum over j aij phi j. Now again we are putting the things within the sum. So I can take it as take this phi I as delta ij phi j. This delta ij is nothing but the Kronecker delta. It means 1 when I is equal to j and 0 when I is not equal to j. And thus we can write the sum as minus k sum over j delta ij di minus aij, and it is nothing but dij. Dij is the dij, or you can say lij rather. How did we define the Laplacian matrix? No, not Laplacian. It's a degree matrix. Sorry, it's the element of the degree matrix dij. So dij minus aij, it is lij. That is the corresponding element of the Laplacian matrix. And if we write it in the matrix vector notation, then we can write it d phi dt equals to minus k d minus a phi. And we have already defined d minus a as L. So it is d phi dt equals to minus k L phi, which is very much similar to the heat equation del 2 phi equals to 1 by k del phi del t, or del phi del t equals to k del 2 phi. And here the matrix L, rather minus L is behaving same as the operator del 2. Thus minus L is sometimes called as the discrete Laplacian operator, and the matrix L itself is called the Laplacian matrix. Now the very next question, why should we study this Laplacian matrix? How is it important? It can be used in the problem of interpolation on graph. Interpolation on graph means, suppose we have a given graph, and at some vertices value of a function are given. Suppose here value of a function is given 2.3, it is 0.5, 1.3, and it is asked what will be the value of the function at the other node. Like interpolation, we have the value of the function at certain points, and we are trying to find the value of the function at some other point based on the values available at our hand. So here also at some nodes value of a function are known, and we are trying to find the value of the function at some other node. And here our aim will be to minimize the sum x at vi minus x at vj whole square for those vi vj's between which there is an edge. And you can see it can be written as xtlx, that is the quadratic form where x is an n vector. The sum xi minus xj whole square can be written as the quadratic form xtlx. That is, the sum is directly depending upon the nature of the matrix L, or you can say the eigenvalues of L. So L is very much important in such problem. It has already been studied by some researcher in 2003. And now it can be applied to complex networks like social networks, or in biological networks like protein-protein interaction networks, or some other kind of complex networks can be analyzed properly using the Laplacian spectrum. Another important application of Laplacian matrix is the Laplacian energy. Actually, graph energy has been come from the chemical graph theory. Chemists have seen that the underlying graph of a chemical compound, if analyzed and if its eigenvalues are computed and the sum of the absolute values of the eigenvalues are taken, then that can very much that can predict the pi electron energy of the chemical compound very efficiently. And it has been seen that if in a similar manner Laplacian energy is considered, for Laplacian energy not only the eigenvalues, absolute values of the eigenvalues are taken, because we will see all the eigenvalues of the Laplacian matrix will be non-negative, so it is meaningless to take the absolute values only. Rather, it is taken as the difference from 2m by n, that is the average degree of the graph, the difference of the eigenvalues from the average degree of the graph, and the sum is taken over all eigenvalues. That sum that is called as the Laplacian energy. This Laplacian energy is also has been found to be very useful in predicting the pi electron energy of the corresponding chemical compound. So these are some applications of Laplacian matrix. Now, about Laplacian eigenvalues of some trivial graphs. As we can see in this example, if you see here, if you just multiply this matrix with 1, 1, 1, 1, what you will get? You see, if you take sum of all elements in any row, it will be 0. It will be 0. So you are getting the 0 vector, that is 0 times all ones. So it happens to be true for every Laplacian matrix. In any Laplacian matrix, all ones will be an eigenvector and 0 will be the corresponding eigenvalue. It is true for any graph. If the graph is an irregular graph, if it is irregular, then all these diagonal entries will be R. It will be R. It will be R, R, R. So this L matrix can then be written as Ri minus the adjacency matrix A. That is, the Laplacian eigenvalues will be R minus lambda I, where lambda is are the eigenvalues of the adjacency matrix. Now, the Laplacian spectrum of complete graph Kn is n minus 1 times n and 1 times 0. It can be shown very easily, because for complete graph, the adjacency matrix is 0 and all ones in the row. And if you consider the Laplacian matrix, then it will be it will be n minus 1, and rest will be minus 1, minus 1. It will be minus 1, n minus 1, minus 1 in this way. Minus 1, minus 1, minus 1, n minus 1. That is, it is nothing but n minus 1 times I minus adjacency matrix. So if we know the eigenvalues of the adjacency matrix of the Laplacian complete graph, then we can find the Laplacian eigenvalues also. And we know the adjacency eigenvalues of the complete graph are n minus 1 and minus 1. N minus 1 1 times and minus 1 n minus 1 times. So from there you can get the Laplacian spectrum of Kn as n minus 1 times n and 1 times 0. Similarly, if you find the Laplacian spectrum of the complete bipartite graph KRR, here we have taken the regular complete bipartite graph, that is on both the partite sets the number of vertices are same, that is equal to R. Then the eigenvalues will be 2R, R and 0 with multiplicities 1, 2R minus 2 and 1. And for the cycle graph Cn, the eigenvalues are 2 minus, the Laplacian eigenvalues are 2 minus 2 cos 2 k phi by n, k equals to 0 to n minus 1. And we see here in all these three graphs, all the eigenvalues are non-negative and 0 is an eigenvalue. Is it true for every graph? Let's see. Yes, we'll be showing it. Before that, we introduce incidence matrix once again. As we know, incidence matrix is a rectangular matrix where the rows are labeled by the edges of G and the columns are by the vertices of G. And the entry in the ij position is 1 or 0 according to whether the vertex J is incident with the edge I or not. And in each row, there will be exactly 2 ones because an edge is incident to 2 vertices exactly. And the number of ones in a column will be the degree of that vertex J. That is the number of vertices, that is the number of edges which are incident to that vertex. Now, we adjust the incidence matrix a bit by changing the first element in each row to minus 1 and the next one will remain same. We call this incidence matrix as the oriented incidence matrix. Let's take the example which we have taken earlier. There are 5 edges, so there will be 5 rows and 4 vertices. The edge A is incident to 1 and 2, so it will be 1, 1, and the rest will be 0. B is incident to 1 and 3, the rest are 0. C is incident to 1 and 4, rest are 0. D is incident to 2 and 4, rest are 0. E is incident to 3 and 4, rest are 0. Now, I'm telling to adjust this matrix by taking the first one in each row as minus 1, this one, and call this matrix B. And this is actually oriented incidence matrix because we are putting an orientation, putting a direction on the edges. Here I am taking the edge A from 1 to 2, that is in this direction. The edge B from 1 to 3, this direction. C from 1 to 4, this direction. D from 2 to 4, Yes, D from 2 to 4 and E from 3 to 4. Yes. So I have actually considered the incidence matrix of an oriented graph corresponding to the given graph. Now we can show that for this oriented incidence matrix B, the Laplacian matrix L can be written as the product BTB, because if we take the ith column, of B as the vector beta I, that is I am taking as beta 1, beta 2, beta 3 and beta 4, then if you take the product, scalar product of beta I with beta I, if you take the product of beta I with beta I, then you see the number of minus ones will be multiplied with minus 1 itself, and when you are taking the sum, that will give you actually the degree of the corresponding vertex. So for beta 1, at the places A, B, C, those will become 1, so beta 1 dot beta 1 will be 3. But if you take the scalar product of beta I with some other column beta j, then it will be 0 unless there is a row in which both beta I and beta j have the non-zero entries. Look here, when we are taking the row B, and suppose I am taking beta 1, beta 2, then this will give you 0, this will give you 0, this will give you 0, this will give you 0. Only you will get a non-zero value here when both the entries in the corresponding column are non-zero, and obviously one of them will be 1 and the other will be minus 1, so the product will be minus 1. So finally, if we take the ijth element of beta transpose B transpose B, that is the product of the column vectors, that will be degree of I if I is equal to j. It will be 0 if I is not adjacent to j, and it will be minus 1 if I is adjacent to j. So if we combine all these products, then we can see L can be written as the product of the matrices beta transpose, B transpose and B. So this is the relation between the Laplacian matrix and the incidence matrix. Now let for any vector x, any n vector x, we suppose bx equals to y. Then if we consider the quadratic form xtlx, then xtlx can be written as x btbx. That can again be written as bx transpose bx. And we have already considered bx equals to y, so it is becoming yty. Y is also an n vector, so yty is nothing but sum of becomes 0 vector. So instead of taking strictly positive sign, we'll have to take greater than or equal to. That is, the Laplacian matrix is positive semi-definite. Its eigenvalues can never be negative. Its eigenvalues will either be positive or it can be 0. Now, how many 0 eigenvalues can we have for the Laplacian matrix? It's given by this theorem. The dimension of the null space, that is the multiplicity of the eigenvalue 0 of Lg, is the number of components of G. That is, if the graph G is connected, then we shall have the eigenvalue 0 just once. And if we have some more number of components in the graph, suppose if we have k components, then the multiplicity of the eigenvalue 0 will be exactly k. And the proof is not very difficult, because if we take x as the eigenvector corresponding to the 0 eigenvalue, then bx equal to 0, and bx equal to 0 means for the vertices ij which are adjacent, for them xi will be equal to xj, because xi minus xj equals to 0. And similarly, for two other vertices jk which are adjacent, for them xj will be equal to xk. So all the vertices which belong to the same component, there is a path. So we can find xi, xj, xj, xk, xk, xl. In this way, we can find a path between any two vertices belonging to the same component. So for the same component, all the vertices will have the same value in every component of the eigenvector x. So that is a scalar multiple of all one's vector, and thus the null space of the Laplacian matrix L contains only one vector, that is the all ones vector, if G is connected. Now, if G is not connected, it has k components, say G1, G2, Gk. Then for each k, let ui be the vector that has all ones in the positions where the corresponding to the vertices present in the component Gi, and zeros elsewhere. Then ui is in the null space of L, and every element of this null space will be a linear combination of u1, u2. Sorry, it is u2. It is u2. And these u1, u2, uk are chosen in such a way that they are linearly independent, because they do have zeros and ones at different positions. They cannot be written as linear. Those cannot be written as the scalar product of the others. So they are linearly independent, and thus the number of vectors in the number of independent vectors in the null space of L will be exactly equal to k. That is the number of the components of G. That is, the number of components of G will be equal to the number of zero eigenvalues of the Laplacian matrix. Now, if the Laplacian matrix, if the graph is connected, then it will have exactly one zero eigenvalue. That is the last eigenvalue. If I put them in order from greatest to smallest, then the last eigenvalue mu n will be equal to 0, and this one will be non-zero if the graph G is connected. But if it is not connected, if it is disconnected, then the number of components, if k, then k such last eigenvalues, smallest eigenvalues will be 0. That's why this second smallest eigenvalue mu n minus 1 of the Laplacian matrix L is called the algebraic connectivity. Because if mu n minus 1 is equal to 0, it means the graph is necessarily disconnected. And if mu n minus 1 is non-zero, then it assures us that the graph is connected. That's why this mu n minus 1, the second smallest Laplacian eigenvalue, is called the algebraic connectivity of G. Another nice application of the Laplacian matrix is that it can be used to find the number of spanning trees of any graph. Obviously, we are considering simple graphs, not multi-graphs. For a given connected graph G with n level vertices, let mu1, mu2, mu n minus 1 be the non-zero eigenvalues of the Laplacian matrix. Then the number of spanning trees of G will be 1 by n times products of all non-zero eigenvalues of the Laplacian matrix. And this is nothing but equal to the equal to any cofactor of the Laplacian matrix of G. If we consider the complete graph Kn, then we have seen that for the complete graph Kn, the Laplacian eigenvalues are, it is here, the Laplacian eigenvalues are here. So if we discard the zero eigenvalue, we have n minus 1 eigenvalues, each of whose values are n. So tau of Kn, it is also sometimes called complexity of the graph itself. It is 1 by n times n to the power n minus 1, and it is nothing but n to the power n minus 2. That is the number of spanning trees of Kn. And it can be proved in many other ways also. Similarly, if we consider all the eigenvalues of the all the Laplacian eigenvalues of the cycle matrix, cycle graph Cn, then we can find the number of spanning trees of Cn is equal to n. And it is also very trivial to check, because in a cycle, if you just discard any edge, then you will get one spanning tree. So you can discard n edges to get n spanning trees. So this is another application of Laplacian matrix, by which we can get the number of spanning trees of any simple graph. And we have already heard in the previous lecture how spanning trees can be applied to real life problems. Now, the inverse of non-zero Laplacian eigenvalues are also very important, because their sum multiplied with the number of vertices gives a quantity called the Kirchhoff index, KFG. And that has actually come from some idea in the Kirchhoff's rule in electrical network theory. If a graph G represents an electrical network in which unit resistors are placed on each edge, the resistant distance means the effective resistance between the vertices I and J, and that is denoted by Rij. And if it is taken, if the sum of all resistance distance are taken, that is called the Kirchhoff index, and it was defined in analogy with the Wiener index, which is nothing but the sum of all distances between every pair of vertices, every pair of distinct vertices. So instead of that ordinary distances, resistance distance were considered by some people, and that Kirchhoff index was defined, and it has also to be seen very much applicable in chemical graph theory. That is, for some chemical compounds, this quantity has been seen to be very efficiently predicting some chemical properties. That's why it is also known as a molecular structure descriptor. Now we'll be considering to find the Kirchhoff index of some derived graphs. Let's define a graph operation which is known as the double graph. Suppose G is a graph with n vertices, v1, v2, vn. Then the double graph will be obtained by taking another vertex set corresponding to the original vertex set V. That is, for every vertex in the graph, we have to take another vertex. And those new vertices will be adjacent to the old vertices in the original graph. Using this relation. One example was already given there, but if we consider a simpler one, suppose I am taking this one, 1, 2, 3. Then, corresponding to these three vertices, we have to take three more vertices, say 1 dash, 2 dash, and 3 dash. Now, 1 is adjacent to 2, so in the double graph, 1 dash will be adjacent to 2. In the original graph, 2 was adjacent to 1 and 3. So in the double graph, 2 dash will be adjacent to 1 and 3. And in the original graph, 3 was adjacent to 2. So in the double graph, 3 dash will be adjacent to 2. This one. In this way, if we consider the double graph of C5, then it will be this one. Another graph operation we have defined, that is called the extended double cover. Here, the main difference is that in the double graph, the original edges were present, and in the extended double cover, these original edges are missing. These original edges will not be considered. the edge set will be ui vi, that is each of the original vertices will be adjacent to the new vertex. These edges as considered, and these edges as earlier. Now we'll find the Laplacian eigenvalues of these derived graphs in terms of the eigenvalues in terms of the adjacency eigenvalues of the original graph. And we are considering the graphs to be regular, because if we don't consider them regular, it will be quite difficult to find the eigenvalues. We can only find some bounds between which the eigenvalues will lie, but we will not be able to find the exact values. So we are considering the graph G to be regular, and then its double graph, we are denoting it by G star, and extended double cover by G double star. Now we denote the adjacency matrix of G by A and that of G star by A star. Since E is real symmetric, then it is diagonalizable. Suppose it is similar to a diagonal matrix lambda, and P is an orthogonal matrix which diagonalizes A. That is API equals to lambda IPI, where PI are the orthonormal eigenvector corresponding to the eigenvalue lambda I. Now we see that the adjacency matrix of the double graph A can be written as A star equals to A0. Check here. Adjacency matrix of A star. Suppose we are taking the first 5 elements as v1, v2, v3, v4, v5, and then the rest 5 for the u's, u1, u2, u5, and the first v5. So in the first block, we'll get the adjacency matrix of the original graph itself, because it gives the adjacency relation between the vertices belonging to the original graph G. Now, because of the presence of the edges of like uy vj, we will have v1 is adjacent to in the original graph v2 and v5, and in the double graph v1 is adjacent to u2 and u5 here, u2 and u5. So here also we'll get 1 and 5. We'll get 1 at these two places and all other places 0. And by the similar reasoning, it can be understood that you will get the matrix A itself here. Again, the adjacency matrix is a symmetric matrix, so you will get A again here, and the vertices in the original graph v1, v2, the new vertices u1, u2, u3, u4, u5, they are not adjacent to each other. They are mutually non-adjacent. So you will have a 0 here. Thus, we will have the adjacency matrix of the double graph as A0. As we have seen that it can be diagonalized, we can write it as P lambda PT in place of A. Now we see that the double graph has 2n vertices if there are n vertices in the graph G, and out of these 2n vertices, n vertices will be of degree R, and the n vertices will have degree 2R. Come here again. The old vertices, those were in the original graph, their degrees will be just doubled, because they have now become adjacent to same number of vertices to the new vertices, same number of vertices of the new group. So their degrees will be just doubled, and these vertices will have exactly same degree of the corresponding vertices in the old graph. So n vertices will have degree r, and n vertices will have degree twice r. Thus, we will have the degree matrix as 2ri 0, 0 ri. And as we have got the adjacency matrix and the degree matrix, we can write the Laplacian matrix of the double graph G star as D star minus A, that is equal to 2ri 0, 0 ri minus p lambda pt, p lambda pt, p lambda pt 0. If we just take the difference, and then we can see that this can be written again as this one. And it is interesting to see that this whole matrix will again be an orthogonal matrix. This is also an orthogonal matrix. That is, if we are able to find the eigenvalues of this matrix, then we'll be able to see, then we'll be able to get the eigenvalues of the matrix L star. Suppose we are taking this matrix as B. Suppose we are taking it as B. That is B equals to 2ri minus lambda minus lambda minus lambda ri. Now we are trying to find the eigenvalues of this matrix B. The characteristics polynomial of B will be given by determinant of B minus xi. So it is of this form. I have just expanded it. And then if we expand this matrix by Laplace rule, Laplace formula, then we see it has only two non-zero elements in the first row. So this is the n plus 1th column. So here in the n plus 1th column, nth row, if we consider, these four elements can be taken to construct a minor, and any other minor of order 2 will be 0 in this matrix. Yes, it has been taken as M2. And if we consider the complement of this minor, then that is also of similar form. That is also of similar form. I'm sorry. So the 2 by 2 determinants, 2r minus lambda 1 minus x minus lambda 1 minus lambda 1 r minus x. Similarly, for all other lambdas, 2r minus lambda 2 minus x minus lambda 2 minus lambda 2 r minus x, and so on. So if we find the values of x by equating each of these 2 by 2 determinant 0, those will be the eigenvalues of L star, and those are given by 3r minus lambda I plus minus square root of r minus lambda I whole square plus 4 lambda I square by 2 for I equal to 1 to n. Similarly, we can find the Laplacian eigenvalues of the extended double cover as 0, 2 into r plus 1 plus minus lambda I plus 1 for I equal to 2 to n, where the lambdas are the adjacency eigenvalues of G. It can be done in a similar manner by taking the adjacency matrix of the extended double cover in terms of the adjacency matrix of the original graph G, and then by expanding the corresponding matrix. Now, if we apply this result to Kn star, that is the double graph of Kn, then we will get plus 1 plus 2 times n minus 1 into 3n minus 2 by 2n minus 3, and the number of spanning trees of Kn star, that is the double graph of Kn, will be 4 times n minus 1 into 4 n minus 3 whole to the power n minus 1. Because we know the eigenvalues of the complete graph Kn are n minus 1 and minus 1. These are the adjacency eigenvalues we are talking about. So if we put the values of these lambda i's in the expressions which we have obtained for the Laplacian eigenvalues, if we put here, then we are getting the, I'm sorry, this is the Laplacian eigenvalues. Laplacian eigenvalues of Kn star are 0, 20 n minus 1 and such and such. And then if you take the product of all those eigenvalues except the 0, if you take the product of all these eigenvalues and divide it by the number of vertex, yes, then that will be the complexity of Kn star, that is the number of spanning trees of Kn star. And also if we take the inverse of those non-zero eigenvalues, take their sum and multiply it with the number of vertices, total 2n vertices are there in the double graph, that will give you the Kirchhoff index of Kn star. On simplification, we'll get this value. But if the graph is not so simple, that is, if its eigenvalues are not so simple, then it will not be easy to find the Laplacian eigenvalues and the Kirchhoff index and the number of spanning trees in such a good expression. In that case, we have also find the Kirchhoff index and the number of spanning trees, that is the complexity of extended double cover of Kn also. Those are giving these values. It is not always possible to find the exact value of the Kirchhoff index, as I have already told you. In that case, people are interested about getting some bound. So these are some bounds given in some recent works, 2015, 2016, where it is seen that the Kirchhoff index is less than equal to n minus 1 into n square minus 3n plus 4 whole by 2. That is, it is of order n cube. But if the smallest degree in the graph, small delta g, is very large, if that is greater than equal to n by 2, then this value will drastically reduce as to 3n minus 1. That is, it will become of order n only. And in an article in 2016, it has been shown that the Kirchhoff index is less than equal to n into delta plus 1 plus nk into n minus 1 plus n square into n minus 2 minus twice mn by k into delta plus 1, where delta is the largest degree and m is the number of edges in the graph. So that is another bound obtained in terms of the number of vertices, number of edges, and the maximum degree. We have tried to compare our bounds, which we will be obtaining using the Laplacian eigenvalues of the derived graphs which we have computed earlier with these bounds. And we have used some earlier results. That the smallest eigenvalue can never be more than minus. Hello? Hello, any problem? Okay, using this result, we'll be able to find the bound. Kf of this star will be less than equal to this one. It is just simple manipulation. Similarly, for the extended double cover, we have also computed some bound. And finally, we have compared the bounds given by Palacios and Pirzada in 2015 and 16, and the bound we have obtained for some graphs. If it is the derived graph of the C5, then we see our bounds are quite close to the exact values. Whereas the bounds 1 and 3, that is of Palacios and Pijadas, are quite high. And what I was telling that if the smallest degree is very high, then the value reduces to 3n minus 1. It is, I have taken the graph of order 30, that is n equal to 30. Then in the double graph, number of vertex will be twice n, that is 60. And this bound is 3 times total number of vertex minus 1, that is 180 minus 1, 179. And our bound is less than that one, that is we have got some better bound. And this has been published in a recent article of ours in Discrete Mathematics Algorithms and Applications. And these are some other references where Godsil and Royal's book on algebraic graph theory is the one of the best book in the literature. And these are the papers which I have already mentioned. So that's all. Now I'll be expecting some questions from you.
Okay, so thank you very much, sir. Actually, your session was very excellent and very informative for the new researcher as well as students as well as academicians. So thank you for your session.
Can I go for questions?
Yes, ma'am.
Yeah, ma'am. Of course, of course.
I have some queries for my knowledge. Thanks. One query is you take incident matrix. Okay, you are taking incident matrix, and then in every row, first one making as minus 1. Okay, and then you are orienting the edges. So, what is the rule to orient the edge?
We are actually taking here arbitrary orientation.
Therefore, I was wondering that the orientation is unique. So once is arbitrary.
No. It's not unique.
It's not.
It's not unique. Just as a convention, we have taken the first one as minus 1.
Okay.
But if it is taken as the second one also, it will make no difference.
Okay. Other one, you have a double graph has been introduced by you?
No. Not by us. It has been studied by many other researchers earlier. We have just taken their definition.
Okay.
And we have obtained the Laplacian eigenvalues in terms of the original graphs.
Okay, that you must have taken the same. No, I don't know. I have not seen about double graphs. There is a splitting graph of a graph, which was given defined in the same definition as a double graph, which was given by Kumar and Goaltore in 1980.
Pardon, ma'am. Please tell me the name once again.
Splitting graph of a graph.
Splitting graph.
Yeah, the same definition. Yes. For a given graph, how to get a splitting graph? You take a
maybe it is known by some other name also.
Yeah. Some people are calling it shadow graph also.
Yes.
Shadow graph. But I would like to understand your definition. Double cover. Double cover of a graph.
Extended double cover, I told you.
Well, extended. Yes, I have not been able to write it down. So how you take the extended double cover of a graph?
It is also been introduced by some other people.
So I can get it.
We have considered. Ma'am?
Can we get it in Google?
I think it will be found.
Okay. If it's found, then I will be interested to find it. I will be interested to know that one. Okay.
Ma'am, I can mail you our some earlier paper in which we have also studied this graph regarding some topological indices, other topological indices, and this time we have considered the Laplacian spectrum of index.
Okay,
So,
I will be happy to get.
and this is also known by some other names. This one is also known by some other names.
Okay, thank you for your knowledge. Thank you, clearing my doubt. Thank you very much for your nice talk.
Thank you,
Actually, we
ma'am.
have some questions from the audience.
Okay,
We
can you
have
please?
some questions. Actually, so is the average degree of a graph depends on to find the eigenvalues of the graph?
Pardon? Average degree?
Average degree of a graph depends on to finding the eigenvalues of a graph.
No, no, no. The average degree is not dependent on the eigenvalues, but the Laplacian eigenvalues have some relationship with that average degree, twice m by n. Because some of the Laplacian eigenvalues can be more than the average degree, and some can be less. But there is no, I think, straightforward relationship between these two.
Okay. So another question comes: is there any graph whose adjacency spectral radius is minimum degree and least eigenvalue is minimum degree? Is there any graph?
Is there any graph whose
Is there
adjacency
adjacency spectral
eigenvalue
is maximum degree?
spectral radius is maximum degree?
Yeah,
Adjacency or Laplacian?
adjacency. I can repeat the question again. So please, is there any graph whose adjacency spectral radius is maximum degree and least eigenvalue is minimum degree? Is any graph exist?
Least eigenvalue will be minimum degree and the largest will be the maximum degree. That's the question,
Yeah.
no?
Yeah.
That is adjacency or Laplacian. What do you want to know?
Adjacency.
That is for adjacency. You used to know lambda 1 plus lambda n goes to capital delta plus small delta. If there is any such graph, or you are exactly going to get the graph for which these two values are equal. Maybe they are. I do not know.
Okay.
Any other questions?
Okay, another question. May I ask you? Another question comes from the audience. So,
Please.
how can we compute eigenvalue of a 2 by 2 matrix when each block is a square matrix?
Eigenvalue of a block matrix where each of the block is a
Each
2 by
block
2
is
matrix.
a square matrix.
There are so many ways you can apply the Sur complement. If all the blocks are square matrices, then determinant of I am writing here. Suppose if you have the matrix A equals to A11, A12, A21, A22, then you can find the determinant of A as determinant of A11 into determinant of A11 minus A12, A22 inverse A21, or in terms of A22 you can also get it. So if you take then you can find the eigenvalues. Is it okay?
Okay. Yeah, okay. So, thank you very much for sharing with us your new views and new ideas. Thanks again.
Okay. Thank you all.
So, we are moving to our So it's time to now moving to our next speaker. So I request Mrs. Moitride to introduce our.
Yes, ma'am. Our last speaker of this session is Professor Hemanto Kumar Barua. Professor Hemanto Kumar Barua is a retired professor of Department of Statistics, Guwahati University, and former Vice Chancellor of Bodoland University, Assam. Now he is associate with Assam Royal Global University, Guwahati, as Professor Emeritus in the Department of Mathematics. He is a very famous name. We are eagerly waiting to hear and learn from about his new invention. Sir, it is our great pleasure to invite you at our webinar. Now it's time to listen from him. Sir, please start your invited talk. Thank you.
Thank you. Nasreen,
Yes, sir.
just display my PowerPoints.
Okay. Sir, it takes some time.
Okay. It is all right. It is all right.
Sir, just a minute. It is ready now.
Okay. Okay, I can see it. So, and then when necessary, I shall just say, then you go to the next slide and so on. So here is my topic for today's discussion. Okay. Good afternoon, everybody. See, 28 years back in 1992, I had observed that if we enter into a dense jungle, the shadow due to sunlight are seen to be different, to be of different levels of darkness. Even inside a room, you may observe that the level of shade below a table is different from that below a bed. Now, I had expressed that mathematically and named it the mathematics of partial presence. Next slide, please. Yes, Nasreen, next. Okay. Now, you see, this is what happened. Only after solving the problem, I came to know that a branch in fuzzy mathematics was already in existence since 1965, and I had no idea about it. Actually, at the time, I was in Goethe University and in the Department of Mathematics only. Some journals of fuzziness were available. Just one journal was there at the time. And I was working in a in the Department of Statistics. I had no idea. Anyway, indeed, I arrived at my results without using any known results of fuzziness. However, the fuzzy sets had been accepted to be outside the domain of classical measure theory. And it was accepted further that the fuzzy sets do not form a field. Now, at these 2 points, my mathematics of partial presence was different from Jare's theory of fuzzy sets. Actually, what happened is this, because I arrived from my own standpoint, so I arrived at something, and then I came to know that this branch is already in existence since 1965. So I had sent it to a journal, Excel Fuzzy Sets and Systems, and they said that, okay, you have done something very new, but then at 2 particular points, you are differing. So good luck, continue your work, etc. Now I have seen that, no, these 2 points are correct, and I continued. I just continued. Okay, Nasreen, next slide. Now, in the language of fuzzy sets, my findings were that 2 probability measures are necessary and sufficient to define the possibility law, or a so-called membership function of a fuzzy number. Secondly, in the theory of fuzzy sets, neither the intersection of a fuzzy set and its complement is the null set, nor the union of a fuzzy set and its complement is the universal set. But in my eyes, the definition of the complement of a fuzzy set was defective. That was the point, actually, because they meanwhile started defining something called fuzzy measure, because not all those postulates that are necessary to define a measure was followed by the fuzzy sets according to them. And again, because according to their definition, a fuzzy set and its complement, if I take say intersection, we don't get the null set phi. Therefore, ultimately, field theory also was not applicable. Next slide, please. Now, those who have been working in the theory of fuzzy sets may not agree with me. In fact, some people have never agreed. But my mathematics of partial presence has been in use in periodic pattern recognition since 2008. And my definition of the complement of a fuzzy set has been in use in clustering algorithms, intrusion detection, and genetic algorithms since 2009. So I have observed that in the realm of computer science, my mathematics of partial presence got accepted, though it could not be very popular in the realm of fuzzy mathematics. The next slide, please. Okay, actually, I'm not very good at making PowerPoints, so sometimes I have just copied from PDF, sometimes I just type. So sorry if you find any difficulty in reading this. Now, here is a set operation I define, the operation of set superimposition. I said, sets of different levels are seen if you enter into a dense jungle. And then suppose if you put an opaque object in front of a small source of light and just put a screen behind it, then you will see umbra and penumbra. So if the level of darkness in the umbra region is taken to be unity, then the level of darkness in the penumbra region should be half, etc. So how to define that mathematically? That is what my aim was, so I had to define this operation. Now we first proceed to define a set operation that we have named superimposition. When we overwrite, the overwritten portion looks darker. This you can very well see if you just overwrite with your pen. So in the overwritten portion, it will look darker. Indeed, in the overwritten portion, there happens to be double representation due to superimposition, which is why that portion looks darker. The operation of union of sets cannot explain this. In fact, it doesn't explain this. When 2 translucent papers with unequal opacities are placed, one covering the other partially, the opacity of in the portion covered by both the papers would be more than the maximum opacity in comparison with the other parts. This also happens due to superimposition. We now proceed to define this mathematically. Next slide, please. Now, defined by the present author, you see, I mean, these citations within the brackets actually should be ignored for now, because as I have said, I have just copied from an article of mine, which was in PDF, so distinct from me. I'm sorry for that. Now, defined by the present author means defined by me, and later used successfully in recognizing periodic patterns. The operation of set superimposition is expressed as follows. If the set A is superimposed over the set B, we get A superimposed over B is equal to A minus B union of A intersection B 2 times. By the 2, I mean actually it represents the elements of A intersection B occurring twice. Then again, union of B minus A. And then, of course, here we have one assumption that A intersection B is not void. We have defined this operation keeping in view the fact that if 2 line segments A and B of unequal lengths are overdrawn, one over the other, that is, this is what we are going to see. Next slide. So it can be seen that for 2 intervals A, this A1, B1, then another interval B with A2, B2, we should have equivalently A1, B1 superimposed over A2, B2 will be equal to A1, A2 union A2, B1 twice union B1, B2 provided A1 is less than A2 is less than B1 less than B2. It is equal to, again, A1, A2 union A2, B1 twice union B2, B1 if A1 is less than A2 is less than B2 less than B1. Ultimately, there can be 4 such types. So I have written all A2, A1 union A1, B1 twice. Then union B1, B2 is under the condition that A2 is less than A1, which is less than B1 and less than B2. And finally, A2, A1 union A1, B2 twice, and then union B2, B1 if this 4th condition is satisfied, that is A2 is less than A1, less than B2, less than B1. Here, actually, before going to the next slide, I would just like to request you to see one thing. Just a closer look now would be needed, actually, to see, to write these things concisely and precisely. Here, A1, A2, you see, are such that A1 is less than A2, sometimes A2 is less than A1. So if we go to see what happens when we go to order them, that will be the next step. Next slide, please. So here, A1 is less than A2, less than B1, less than B2, then A1 less than A2, less than B2, less than B1, etc. are the 4 different possibilities in this case. So here we have assumed, of course, as I said earlier, without loss of any generality, that the intersection of A1, B1 and A2, B2 is not void. Means there should be at least 1 point in this. In other words, the maximum of AI is less than or equal to minimum of BI for I equal to 1 to 2. And in that case, here comes the ordering. Indeed, then we can see that superimposition of A1, B1 and A2, B2 is equal to, in this short expression, I have written A1 within bracket, that 1 is within bracket. I mean, symbolically, that's what I've written. A1, comma A2, union A2, comma B1, with index within bracket 1. It is coming twice, then union B1, comma B2, where A1 is the minimum of A1, A2, as I said, ordering. Please, in the next slide. This is A1. Then A within bracket 2 as index is equal to the maximum of A1, A2. Similarly, B1 within bracket is minimum of B1, B2, and finally B2 is maximum of B1, B2. Now this conversion in terms of ordered values is to be noted very carefully, very properly. We'll soon see that the applicability of this conversion in defining the randomness fuzziness principle. That is due to me. So in this way, for n intervals, now this is only for 2 intervals, for n intervals, like A1, B1, A2, B2, and etc. up to A and B, and subject to the condition that their ultimate intersection, A1, B1, intersection A2, B2, etc., finally, intersection of A n minus 1, B n minus 1, intersection A and B n is not void. Next slide, please. Yes, next slide. Okay. So ultimately, this is what we get. A1, B1, superimpose over A2, B2, etc. Finally, superimposed with A and Bn gives us this. Here, A within bracket 1 means it is the minimum of all A's. Next is A2. And similarly, so it comes A1, A2, union, A2, A3 twice, and so on, and so on. And finally, at last, you know what will happen? Like A n minus 1, A n will occur n minus 1 times. A n B1 will occur n times. Because it is not void after all, as I have shown. And then B1, B2 will occur n minus 1 times, and so on. When it is increasing from 1, 2, 3, 4 up to say, n minus 1, n, and then it is coming down again, n minus 1, then 3, 2, 1. This is what I'm ordering. When A1, where A1, A2, An, etc. are values of A1, A2, etc. arranged in increasing order of magnitude, and B1, B2 up to Bn are values of, once again, B1, B2 up to Bn arranged in the increasing order of magnitude. And for example, A n minus 1, A n minus 1 means within bracket A n minus 1, this in this index represented n minus 1 times. That's why I have written like that. Elements of A n minus 1, A n represented n minus 1 times. Observe it. Order statistical matters can now enter into our discussion on superimposition. I mean, this is how I define the operation of set superimposition. And now, ultimately, in the realm of statistics, those who have studied statistics may not be in the BSc level, but beyond that, actually, there will always be one particular chapter called order statistics. So I will just mention that. Okay, next slide, please. Here from, actually, I have written clearly again. Now, an application of the operation of superimposition of sets. We now proceed towards an application of the operation of set superimposition. I'm repeating again, when we overwrite, the overwritten portion looks darker for obvious reasons. Double representation creates a doubly dark situation in the common portion. Now, if the level of darkness in the common portion is taken to be unity, as I said earlier, then that in the other portions would have to be partial. Next slide, please. Once again, it is from PDF, so not very nicely visible, but anyway, let me continue, please. So for n fuzzy intervals, now here actually, I have used the word fuzzy for the first time. As I said, when I worked it out at the time, I had no idea that there is something called fuzzy mathematics since 1965, when I was in school, actually, in a lower class in 1965. And I somehow, unfortunately, didn't come to know about its existence. So then, when I ultimately came to know in 1992, 1993, that this branch is there anyway, so I borrowed this word from them, fuzzy. And now, in my talk now, for the first time, I am using this word fuzzy, because it was already in existence. So Now let me come back to the discussion. For n fuzzy intervals, A1, B1, with level of presence, that is in my words, the level of presence 1 divided by n. Earlier, we talked about A1, B1, A2, B2, etc. Now let us make it 1 by n for everything. A1, B1, 1 by n, then A2, B2, once again 1 by n, A and B and 1 by n. Now if I take, superimposition of all these intervals, you see this is what we will get. When we superimpose A1, B1, then A2, B2, etc. The result was, that means the equality in the earlier slide was, Nashun, can you go back to the earlier slide, please? Once. No. Yes, this one. No. Next. Here. So this is the problem.
So this one.
No, next one. Just the next, not earlier, but next. Go ahead. Next. No. You are going backwards. I'm talking about coming forward. Only the last slide. Just one more step. Here. No. Here actually this is for fuzzy intervals. Okay. There seems to be a confusion while going back. So what I mean is, earlier it was A1, B1, then superimposition A2, B2, etc. Now I'm superimposing A1, B1 with a level 1 by n. Earlier it was with level 1. Now all these intervals are of level 1 by n. That gives me, instead of A1, A2, which 1, the present level 1, it will be 1 by n. So earlier A2, A3 was with level 2. Now it is 2 by n. That is what I'm saying. So finally, it will increase from 1 by n to 2 by n, then n minus 1 by n, then 1, and then it will start coming down, n minus 1 by n, etc. Finally, 2 by n, 1 by n. Here, for example, B1, B2, B within bracket 1 as index, with level of presence n minus 1 by n represents the uniformly fuzzy interval. Here also I am using the word uniformly fuzzy, means all equal, 1 by n. It was all equal, 1 by n. So uniformly fuzzy intervals B1, B2 with membership n minus 1 by n in the entire interval, like A1, A2, A being the values of A1, A2, etc. arranged in the increasing order, as I said earlier. And this is similarly, B1, B2, etc. also are being arranged in the increasing order. Go to the next page, please. Next slide. Okay. Now consider just a bit of simple mathematics again. Consider now two spaces, say omega 1, A1, pi 1, and omega 2, A2, pi 2. Here, omega 1 and omega 2 being real intervals, alpha, beta, gamma, respectively. And let x1, x2 up to xn, and y1, y2 up to yn be realizations in alpha, beta, and beta, gamma, respectively. So for n such equally fuzzy interval, equally fuzzy means all which, fuzziness level 1 by n. All with fuzziness level 1 by n. Okay, x1, y1 with 1 by n, x2, y2 with 1 by n, etc. So ultimately, that will give us the membership value. I said, please observe the word membership value, I said. Okay, later on, this reference will come. Why I have said value. It is 1 by n everywhere, and we will get this. Earlier it was with A1, A2, now I'm writing with x1, y1, x2, y2. Means x1, x2, xn, etc. are from the first space, omega 1, A1, pi 1, and y1, y2, etc. are from the second space, means omega 2, A2, pi 2. Okay. Next slide, please. Yes, next slide. So ultimately, this is the last line. It came. It will be reducing, as I said, from n minus 1, from n by n, that is 1, then n minus 1 by n, etc. Finally 2 by n and 1 by n. It is a step function. First it increases from 1 by n, 2 by n, etc. to n minus 1 by n, then n by n. And then it comes down again from n by n, downwards to n minus 1 by n, n minus 2 by n, and finally 2 by n to 1 by n. Where, for example, this 1 y1, y2, n minus 1 by n represent uniformly fuzzy intervals y1, y2 with membership value n minus 1 divided by n in the entire intervals. And as earlier I was using the symbols a1, b1, etc. Now I am saying this x1, x2, etc. are values of x1, x2 arranged in increasing order of magnitude, and y1, y2, etc. also are in arrays. In increasing order of magnitude. Now let us recall. Means it was mentioned in that particular article from I have copied this. However, that the fuzzy intervals, once again the word fuzzy I am using because the branch was in existence already. So for the fuzzy intervals, x1, y1 with a level 1 by n, x2, y2 with a level 1 by n, and so on up to xn, yn with a level 1 by n, all with uniform membership. Uniform means 1 by n, equal. The values of membership of the superimposed fuzzy intervals are 1 by n, 2 by n, then n minus 1 by n, then 1, then n minus 1 by n. It comes down again. So these values of membership are in two halves. Please go to the next slide. I cannot read it. It has become too small suddenly. Okay, make it slightly larger. That will do. You see, this is the sequence. 0, 1 by n, 2 by n, n minus 1 by n, then 1. For the values of x, that is x1, x2, etc. And similarly for y. It is first it is 1, then n minus 1 by n, then it just gradually decreases step by step. It comes to 2 by n, 1 by n, and then 0. This would suggest that that they can define these things, this 0, 1 by n, 2 by n, etc. Now, those who have studied this thing called order statistics, if for some people it is new, it is all right. I'm just explaining. We have found these things from order statistics. Now, they are order absolutes. I mean, these things will suggest that they can define an empirical probability distribution. And by empirical probability distribution means the distribution function is such that it increases from 0, goes to a maximum of 1. If it is in the discrete case, this is how it might increase. 0, 1 by n, 2 by n, etc. Because my ultimate aim is to see what happens when n becomes infinitely large, n tends to infinity. So till that happens, till I take a limit of n tends to infinity, I would call it the empirical in the probability distribution. And the next one is a complementary empirical probability distribution because it is 1 minus, as you can see. First it is from 0 to 1, it is increasing, then it is coming down from 1 to 0. That's why the first one is a probability distribution, empirical of course, and the second one is a complementary probability distribution, once again empirical. In other words, the realizations of values of this x in increasing order and y is in decreasing order, we can see that if we define, now please, next slide. Next slide, please. Somehow I'm seeing it in a very small thing. Can it not be made a bit larger? Acha. Okay. I should be able to read, and others should be able to see. You see, these are the functions I have defined, like say this psi1 x equal to 0 if x is less than x1, means outside our intervals it is 0. Then it is r minus 1 divided by n if my x lies between x, r minus 1, to xr for r equal to 2, 3 up to n. And it will be equal to 1 if x is greater than or equal to small xn. And similarly for phi y. Now, the psi1 x was increasing from 0 to 1. Psi2 y will decrease from 1 to 0, as you can see in the slide. So it is at the first value, if it is less than y1, if y is less than y1, it is equal to 1. No. Let me see. Okay. And then it is 1 minus r minus 1 by n for r equal to 2, 3 up to n. And finally 0. As soon as it goes out, means y is greater than yn. So then we are assured that psi1 x will tend to, means when I take limit as n tends to infinity, to a particular probability law, from the empirical distribution function, it goes to the theoretical distribution function pi1 alpha x lies between alpha to beta, and psi 2 y, it will be turning to 1 minus pi 2 beta y, where y lies between beta and gamma. Actually, this is a particular law known as the Glivenko-Cantelli theorem in order statistics. It's a very important thing actually in the theory of distribution. Statistics have become very classical, and now people, maybe they do not show much interest. Anyway, next slide, please. So we have just seen that the existence of two densities, d psi 1 dx and d psi y dy for x lying between alpha beta, y lying between beta gamma, is a sufficient condition to construct a fuzzy number alpha beta gamma. This is the matter. This is the matter. I have seen from my angle, and I have seen that ultimately two measures actually, two probability measures, or rather two Levi-Steele measures are sufficient to define a fuzzy number, to construct a fuzzy number. Now, I have used the word construct in this particular slide, at least for the first time. You know what happens? Those who have been studying the theory of fuzzy sets, and they are working also on it, they never say how to construct a fuzzy set. Please note this point for those who are interested. They never say how to construct. They just assume the function and they continue. Where from does it come up? They never say that. Because from that standpoint, they cannot say that. But as my standpoint was very different, somehow I arrived at the theory of fuzzy sets is another matter. So it is a sufficient condition to construct a fuzzy number. We can now summarize our findings as follows. If psi 1 x and 1 minus psi 2 x are two independent distribution functions defined in alpha beta and beta gamma respectively, then the membership function of a fuzzy number n, of course, this should be called actually a normal fuzzy number. That's how they define, because the maximum value is equal to 1. The n is equal to alpha beta gamma can be expressed as mu nx equal to phi 1x if x lies between alpha and beta, is equal to, means mu nx is equal to, again, psi 2x if x lies between beta and gamma, and 0 otherwise. The 7, 8 are here, you can please ignore them. Next slide, please. Please go to the next slide. Okay, so thus the existence of two uniform densities, the simplest form of all densities, in the intervals alpha, beta, beta, gamma, is sufficient for the construction of a so-called triangular, I said so-called, triangular fuzzy number alpha, beta, the simplest form of all fuzzy numbers. If you read books on, let's say, fuzzy mathematics, actually they're classical ones, they will simply say that the triangular fuzzy number looks like this, they will just form a triangle, etc. And why has anyone gone for using the triangular fuzzy number? If you ask anyone, they will say that this is the simplest. Simplest is another matter, because it has come from these two, simplest kind of densities in the statistical realm. Two uniform densities. This is the simplest. That's why ultimately two uniform laws give rise to a triangular fuzzy number. The left part is defined by my, say, the distribution function, and the right part is defined by the complementary distribution function, according to me. Now, other kinds of densities also it is sufficient accordingly to give rise to other kinds of fuzzy numbers. We are starting the assumption that two densities, and hence the assumption of two distribution functions in alpha, beta, and beta, gamma would give rise to a fuzzy number. It can be expected that defining a fuzzy number is in this way would be helpful in explaining fuzzy arithmetic in a much simpler way. Next slide, please, so that there is no doubt in time. Next slide. So here, not one, and hence not one but two densities with reference to two probability measures defined on two disjoint sets can construct a fuzzy membership function. For this, however, one needs to look into the matters through application of the Glevenko-Cantelli theorem of order statistics on superimposed uniformly fuzzy intervals. The distributions may be geared to the major theoretic definition of randomness. What you mean is that the variable concerned need not be associated with any error term in statistics. Actually, what I mean is the major theoretic definition of randomness simply says that the notion of probability doesn't enter into the definition of randomness. And so, anyway, we shall get it later. So please, next slide. I may be in time trouble. So the membership function of a fuzzy set defines the concerned possibility distribution. It is also known as this. The possibility distribution is also called the membership function, please. And it is known that if f omega and p omega are the possibility distribution and the probability distribution respectively defined on omega, one cannot infer f omega and p omega from each other. So various authors have tried to link probability to possibility without success because they have taken this particular thing for sure that within the same interval they can define a fuzzy law as well as a probability law. Now we have already answered as to why they did not succeed in linking probability to possibility. We have, with the help of this set operation called superimposition and using the Glevenko-Cantelli theorem on order statistics, established that fuzziness can indeed be linked to randomness. But we show that not one but two probability distributions are needed. They were trying only one. Okay. I mean, in other words, we could be able to conclude that there is no logical reason. There is no logical reason why one p gamma should be imposed on a gamma on which f gamma is already defined. A fuzzy law is already defined. Why should we go for a probability law? If time permits, I'll tell it later, please. Okay, go ahead. Next slide. Next slide. We have therefore arrived at our answer to the question which we have raised earlier. That you see this omega 1 A1 P1 and omega 2 A2 P2, where omega 1 and omega 2 are the real intervals A, B, and B respectively, can define a possibility space, which is, say, omega equal to omega 1 union omega 2, represented by the fuzzy number, the normal fuzzy number A, B, C. Okay. Okay, next slide. Next slide, please. Srini. Next slide. Okay. Here is the question I'm just raising about randomness. This is what major theory says. Suppose we define this capital Fx equal to the integral from a to x fx dx, and then dfx dx is equal to my small fx. Now, any function fx whose derivative is equal to fx is a primitive or an indefinite integral of fx. Thus, the definite integral regarded as a function of the upper limit of the integral is a primitive, etc. Now, according to the Dubois-Pradet definition, that means after Lopchi-Zadeh defined the fuzzy numbers, Dubois and Pradet added one particular definition. They call the left function a left reference function and the right one as a right reference function. But they did not go beyond that. Next slide, please. If they would have seen, yes, next slide, please. If they would have seen actually where from that comes, then the things would have been, I'm very different. Okay. Here, if d psi 1x dx is suppose small psi 1x, I mean small phi 1x, then a to b, suppose because we are defining x in a to b, it is equal to 1. Now, that is the definition, the major theoretic definition of randomness. This small f phi here is a density function. It is simply called density function. It needs to be a probability density function. We will come to that later. Please, next slide. Next slide, please. So, this is the Dubois-Pradet right reference function and complementary, etc. Now, therefore, a possibility space can be defined on a triad ABC, etc. Okay, wait here. Now, wait there where you were already. Next one, please. Next slide. Next slide, please. Yes. Here, as you can see, my small fx in the earlier slide was 1 by b minus a. Similarly, this gx is 1 by c minus b for x like between b and c. So I can define this, capital Gx like x minus b by c minus b and so on. So it can be seen that fx is the left reference function. Means the word that they did define, just they gave the name. It is called the left reference function. What I am saying is that the left reference function is a probability distribution function. And similarly, they define the right reference function also in my eyes. Here it is 1 minus gx. It is a probability distribution function, of course, a complementary probability. Next slide, please. Next slide. Okay, so in fact, just as the theory of probability is the simplest continuous probability law in the equivalently triangular fuzziness is the simplest possibility law. In other words, what we are trying to assert is found to be satisfactory from the standpoint too. So we use triangular fuzzy numbers not just because they are easy to handle. They are in fact the simplest possible normal fuzzy number arising out of the simplest possible probability law. And here I have just tried to form a link between a possibility or the membership function and the probability laws. Next slide, please. Yes, next slide. So we have found these three things, actually, conclusions. That trying to impose one probability law over an interval defining a possibility space is not correct. We need two and not one probability space to define a possibility space. On the other hand, given a possibility space, it can be bifurcated into two probability spaces always. Hence, the major theoretic matters of possibility may be geared to forming two probability measures. Next slide, please. This is A, and B is here. I have actually framed the in my eyes this is the correct randomness fuzziness consistency principle. On the right hand side, there are two probability laws, and in the right hand side, there is a possibility law, and they can be linked. Next slide, please. And finally, trying to impose a probability law on the same interval where a normal fuzzy number has been defined, and to try to find a principle of consistency between probability and possibility is not logical. I mean, that's what they were trying. One probability law, to be transformed to one possibility law. Now, constructing a probability law from the knowledge of the membership function of a fuzzy number doesn't make sense. If one is not satisfied with applying probabilistic mathematics, then they can apply in fuzziness. And where exactly to apply fuzziness, I shall say if time permits. Please go to the next slide. I may be in dearth of time. Please go to the next slide. Okay. We have shown, okay. In the name of constructing, at the same time, what they were trying is, they were trying to bring in probability theory as something that can be found from the, fuzzy law straight away. But they were trying to construct one probability law. That was the point. It should be two. Next slide, please. Now, this one, I cannot see the initial things. Please show me the entire slide. Please show me the entire slide. Entire slide. Okay. The complement of a normal fuzzy number. A bit in a large way, please. I cannot read it properly. Okay. The complement of a normal fuzzy number. According to the Jadahian definition, if a normal fuzzy number alpha, beta, gamma is associated with a membership function mu and x is equal to, say, f phi 1 in alpha beta and phi 2 in beta gamma, and zero otherwise. The complement he defined as simply 1 minus phi 1x everywhere. Simply 1 minus phi 1x means if phi 1x is the membership function from alpha beta to gamma, alpha, beta, gamma, is simply, Jade defined this as 1 minus phi 1x. Then what happens is that in a particular, say for a particular number ABC, if you define its complement as again a number ABC, with the membership value 1 minus phi, then see what happens. Next slide, please. Next slide. Yes, next slide, please. Okay, now I am giving two counterexamples. This is the first one. Okay, counterexample 1. First, we would like to ask the readers a simple question. Can a statement and its complement ever be the same? Common sense says that the answer is negative. Consider now the set of real numbers with constant fuzzy membership function equal to half everywhere. Therefore, according to the Jadahian definition, its complement too will have the constant fuzzy membership function equal to 1 minus half, because is it 1 minus pi, is it? So 1 minus half equal to half everywhere. Next slide, please. Next slide. Okay, in other words, here is an example of a statement defining a fuzzy number. Now, that statement defined a fuzzy number, and that statement defined its complement. Now, which is exactly the same as the statement defining the complement, you see. Both which, membership and half. So the statement is same as its complement. Accordingly, if the Jadahian definition of the complement of a fuzzy set is true, we have arrived at a contradiction that a statement and its complement can be the same. Some people might still argue that half truth is half wrong too, and therefore they are equivalent. We therefore proceed to cite a second counterexample. Please go to the next slide. This is the second one. Now we'd like to ask the readers another simple question. Can a statement ever include its complement? The first question was, can they be same? Now, can the statement include its complement? Now, once again, common sense says that the answer is negative. Consider now the set of real numbers. See my example. With constant fuzzy membership function, that means the fuzzy membership value I'm telling, equal to 3 by 4 everywhere. Therefore, according to the Jadahian definition, its complement will have the constant fuzzy membership function equal to 1 minus 3 by 4 equal to 1 by 4 everywhere. Please, next slide. Next slide, please. In other words, here is an example of a statement that actually includes its complement. Means you have a statement and it's include its complement. Accordingly, if the Jadahian definition of the complement of a fuzzy set is true, we have arrived at a contradiction that a statement can include its complement. That's why I said that this particular definition had to be changed. Okay, next slide. Next slide. Hello. So our counterexamples are based on the fact that if a glass is partially filled with water, then the height of the empty portion is to be counted from the height up to which the glass is partially full. These two counterexamples should be enough to establish that the very definition of complement of a fuzzy set is wrong. Otherwise, we wouldn't have got these two counterexamples. Next slide, please. Next slide. In fact, here, logic has been forced to follow mathematics. Who is the error then? In fact, fuzzy membership function and fuzzy membership value are two different things. But in the Jadahian definition of complementation, these two things have been taken to be the same. Means for a fuzzy set, suppose they have defined the fuzzy membership function for the complement of the fuzzy set. Actually, when they simply take 1 minus the membership, that is not the function anymore. It is the fuzzy membership value. That's what I'm saying. The fuzzy membership value and fuzzy membership function are not same. Next slide, please. Why they are not same? We shall explain. Here is the thing. This is a fuzzy set. Say membership value given it is shown, and for the complement, it is simply outside this set. So membership value for the given x in the complement, this arrowed portion you can very well see, and it goes for the entire interval from minus infinity to infinity. Okay, next slide, please. Please go to the next slide. So let actually mu1x and mu2x be two functions such that mu2x is less than mu1x, both lying between 0 and 1. And then we have seen that we have to consider the difference, this mu1x minus mu2x as the fuzzy membership value, not fuzzy membership function. So we have to count from this. Next slide, please. Oh, they have become too big for me to read again. Okay. We therefore had put forward an axiom regarding the complement of a fuzzy number and a theorem to describe the membership function of a fuzzy number. The theory of fuzzy sets does not say anything about how to construct a fuzzy number. Fuzzy membership function can actually be constructed. Come, next slide. Next slide, please. Yes, the axiom is based on the following fact. I will just show an axiom. You see, not everything can be counted from the 0 level. It's as simple as that. Everyone knows it. But while defining the complement of a fuzzy set, actually this particular simple thing was ignored. Just take this example. If a 6 feet tall man stands on a 3 feet high table, the height of the person does not become 9 feet, because the height of the man has to be counted not from the ground level but from the table as a reference for counting the height. That's what I'm saying. That it is not true that you have to you have to count everything from the level 0. Sometimes the level is different also. Here is a thing. Let a man stand on a table and his height doesn't increase, because in that case the reference will be different, not the ground level. Please, the next slide. So now fuzzy vectors, I'm just referring to this. Fuzzy vectors have been studied almost since the beginning. However, just as fuzzy number has to be defined with reference to a membership function, every fuzzy vector also has to be defined with reference to a membership surface. That nothing, however, is available in the literature other than a few of my works, okay? In the literature about the membership surface when a fuzzy vector is defined as y. Next slide, please. Next slide, please. See, to be able to define the membership surface of a fuzzy vector, we would need to know the physical significance of the left reference function and the right reference function of a normal fuzzy number. Only we have said that the left reference function is a distribution function and the right reference function is a complementary distribution function. So from the majority standpoint, they can be multiplied, and this multiplication does have some meaning, some physical significance. Otherwise, the functions they are defined, left reference, right reference. But if they have to multiply, then what is the physical significance? They cannot say that. Okay, please come to the next slide. Next slide. Yes, to define a membership surface, we need to define the product of the left reference function, Lx. I said L, left. And suppose another number is there, a real number, so Ly, and means these Lx, Ly are the left reference functions, and the right reference functions are Rx and Ry, and the two normal fuzzy numbers are given as X and Y. Now, in our way, we can define the products such as Lx, Ry, for example, because they are probabilities. In the theory of fuzzy sets, this kind of a product does not have any physical significance. Therefore, it will not mean anything. You will just multiply two functions. There should be a physical significance. There should be a reason. Please, next slide, please. So this was my axiom 1. The fuzzy membership function of the complement of a normal fuzzy number n is equal to 1 for the entire real line with the membership value counted from the membership function. Means A is something, the fuzzy number A is something, A complement is something else. A complement simply starts from -infinity to infinity, and the fuzzy membership function is always equal to 1. You have to count from the membership function mu x of the original number n. Next slide, please. And this was my theorem, as we have already mentioned, that for a normal fuzzy number and alpha, beta, gamma, and membership function mu and x as psi1 in alpha, beta, and psi2 in beta, gamma, and 0 otherwise, such that psi1 alpha equal to psi2 gamma equal to 0, etc. Then psi1 is a distribution function of a random variable. Random, I said, in the measure theoretic sense. It's a random variable defined in the interval alpha, beta, and psi2 is a complementary distribution function of another random variable defined in the interval beta, gamma. Next slide, please. Now things are getting simpler. Here you see how I said superimposition. Suppose if you just travel somewhere, say, on a highway, suppose ultimately say some electricity poles are lying one over the other. It is something like this. You put one translucent paper over another. It looks something like that. So here I am taking 3. And that's why x1, y1, 1/3, x2, y2, 1/3, x3, y3, 1/3. Please, next slide. From above, next slide. This is what the picture look like. See, slowly the cumulative and complementary cumulative distribution function can be seen from 0, 1/3, 2/3, 1, then 2/3, 1/3, 0. And this is the discrete Dubai-Paré left and right function. This is what they define, but they simply stopped short of going any further. They just said reference function. They didn't mention to the probability things. I said probability measure. Okay, next slide, please. Next slide, please. Yes, Nasrin. So these are my realizations. Okay, I'll just go very fast. Establishing a new theory is tough, and making changes in an existing theory is tougher, particularly when the changes are suggested in a field that had originated from more than half a century ago. Now it is 2020, it was 1965, that's what I said. And hundreds of books and thousands of articles have meanwhile been published in that field the world over. Next slide, please. Next slide. So in the theory of fuzzy sets, it was accepted that the fuzzy sets do not conform to the major theoretic formalisms. Secondly, it had been accepted that given a fuzzy set, neither its intersection with its complement is the null set, nor its union with the complement is the universal set. Next slide, please. Next. In fact, in the theory of fuzzy sets, not always logic was followed by mathematics. It had mostly been the other way around. Logic should be followed by mathematics. Any mathematics. First comes logic, and then mathematics should follow it. But without trying to understand any head or tail of what you are doing, if you just do some XYZ, some kind of calculation, integration, differentiation, and then try to impose some logic on it, that's a pure nonsense in my eyes. That's what I say. We all know that when we overwrite, the overwritten portion looks darker for multiple representations. The operation of union of sets does not explain multiple representation. So we define a set operation called separation of sets. Next slide, please. Then we observed that to explain the presence of different shades of darkness in the umbra and in the penumbra regions of the shadow on a screen when an opaque body is placed in front of a source of light, we need to define partial presence of elements in the set. Next slide. Next slide. So from multiple representations, we arrive at partial presence of elements. We quantify the level of maximum darkness in the shadow as unity. So that if the level of presence of darkness in the umbra portion is 1, then in the penumbra portion it will be half. And this we can see. Even say high school physics books, it is there, umbra, penumbra. So levels of darkness are different. It's a very simple observation. Next slide, please. So thereafter, coming back to the example of overwriting, we observed that if we superimpose n equally fuzzy, I have to say equally fuzzy because that concept was already there, intervals, each with membership 1 by n. The standard formalisms of order statistics come into play automatically. We then found what had been already known as the normal law of fuzziness could be explained with the help of 2 laws of randomness that could be defined using a classical theorem on order statistics, means the Glevenko-Cantelli theorem. It is there. It has been there since long. We could thus naturally arrive at defining fuzziness with the help of 2 laws of randomness. Next slide, please. Next slide. We didn't have to ponder over how to express randomness in terms of fuzziness. It means the other people were trying to do that. They have studied fuzziness and they were trying to, impose one law of probability on the same, space. That was the problem. That was the root problem. And in my eyes, there was no need to do that. In our case, we did not start with an idea that the concept of fuzziness is a competitor of the concept of randomness. The standpoint of the mathematical workers in this field had always been and still is that a given law of fuzziness could possibly be linked with one law of randomness, and that is how they have been trying without success to link randomness with fuzziness till this day. Please, next slide. Next slide, please. I don't have much time, I suppose. Please, next slide. Okay. The Glevenko-Cantelli theorem deals with establishing a limiting probability law from an empirical probability law. This theorem, like all other in probabilistic formalisms is true in the broader measure theoretic sense too of defining randomness. Unfortunately, at that juncture, the question of examiners closing their diplomas, if a particular examinee is allowed to get through, came into picture. And we decided, without much fuss, to publish our findings locally so as to keep a claim should the need arise later. What I mean is, let me explain. We all know that when we write a paper, when we write an article, we send to a journal, and the journal editor or the editorial board will send to some, referees, now it is called reviewers, to examine the validity of the research whatsoever. Now the thing is, suppose I'm asking the teachers here, because the viewers are mostly teachers, I hope, and professors, etc., are all here. If suppose a student of yours gets a master's degree in mathematics, if that be a condition that you lose your MSc degree, would you accept that? Will anyone accept this? I had been a teacher all life. Now, would I have possibly accepted this? That suppose say one of my students get his master's degree, and that on that particular day my degree will be dismissed because he has got the degree. Then what will happen? The examiner will not actually give a, that means ultimately he will fail the examinee. That's what happened. That's what happened with me. I was telling the truth, but the examiners were telling something else. I was going to the west and they are going to the east. So my findings were simply rejected. It continued to be rejected, so I published it in a local journal where the referee was convinced and it was published. That was in 1999. Then in 2008, please come to the next slide. Please come to the next slide. And see, this is the matter. In every strife between scientific logic forwarded by one single individual and baseless belief coupled with collective arrogance of all others concerned, logic had always been the instantaneous loser. Just remember about Galileo. He supported Copernicus and he was facing death because Copernicus was true after all. The universe is heliocentric, but the earlier idea was that the universe is geocentric. Once someone said something, it was a gone case. So this happened many a time in the history of science. In fact, here the Gödelian theorem of incompleteness, arguing that no logical system itself can ever prove that it is true, came out. While remaining within a system, it is impossible to disprove an axiom included in the system. You have to look into the thing from outside. Please, next slide, please. Next slide. Next slide, please. Nasrin, so as to find a flaw in a logical system, one has to look into the system from a perspective outside it. And to appreciate a logical flaw in a system, one therefore has to come out of the system first. I didn't have to come out because we already started with the idea of superimposition. I did not know that the theory of fuzzy sets was in existence in 1965 when I came across this problem in 1992. So we started with the idea of superimposition of sets with constant partial presence and arrived at Jadeh's definition of fuzzy sets. Nowhere did we use any Jadehian axiom while defining our randomness, fuzziness, consistency principle. We deduced our results remaining wholly outside the existing system. Next slide, please. Next slide. Nasreen? Acha. So while in our eyes, the assumption of being able to infer a law of randomness from a law of fuzziness was absolutely absurd. In the eyes of those who had been working on fuzziness, it was obviously difficult to digest because they were referees. That the normal law of fuzziness is rooted at two laws of randomness, because as soon as they accepted all their works that they have done earlier would have to be cancelled automatically. Why will they do that after all? Indeed, the Gödelian definition of incompleteness, excuse me for my arrogance, but this is what happened in my life. You see, this is 2020. And I had been talking about 1992. I was very young at the time. My pedestal was small. I was simply a reader at the time in, say, Guwahati University, and I was, in fact, contesting with a professor, Lord P. Jadeh, for MIT. I mean, I was just a silly contestant. So nearly a decade later, we used our operation of set superimposition towards recognizing calendar-based periodic patterns, and we were very highly bemused. I was very highly bemused to observe that our findings got positive note from the examiners. Why? This time the examiners were from a different system. We there used the definition of superimposition of constantly fuzzy sets, and they readily agreed that there was nothing wrong in doing so. Next slide, please. Next slide. So the readers can verify for themselves that this set operation proposed by us back in 1999, published in the Journal of the Assam Science Society, I said the local journal, has been in use since 2008 in pattern recognition without any objection from anyone. That settled the issue that our definition of set superimposition was indeed firmly footed. Next slide, please. I think we are coming to the end. Next slide, please. To define partial presence, we thereafter used the Levenko-Cantellier theorem on superimposed constantly fuzzy intervals, and this theorem is something very classical in the statistical literature. But one has to know about it, that it exists after all. In other words, we understood that our definition of partial presence of an element in a set, better known as fuzziness since 1965, must necessarily be correct. Next slide. Am I coming to the end? I have forgotten. Please, next slide. So here then is an example of a theory that has been declared unacceptable by those who have been studying something that was precisely the opposite of what the theory wanted to describe. But an application of a part of that same theory was found to be acceptable by another set of people who were not insiders of that realm more than a decade later. One conclusion was evident. If we are found correct in 2008, we must have been correct more than a decade earlier too. Come, next slide. I think only this. So at this point, we would like to remind the readers, actually, it was a copy, remind the viewers. One important but generally misunderstood point regarding the definition of randomness. Anyway, this can be neglected. I said that the majority definition of randomness is different from what is usually presumed. Please go to the next slide. Next slide. This is not very important. This may be of interest to some of you. If for a function fx defined in AV, the integral of fx from a to b is equal to 1, then classical measure theory says that x is a random variable and fx is a density function. The notion of probability does not enter into the measure theoretic definition of randomness. What I mean is that not everything random has to be probabilistic. Okay. Next slide. Next slide, please. We observed that in the Zarihan definition of complementation, membership value and membership function had to be taken of same meaning. If a glass is half full, it is also half empty, but the empty portion has to be counted from half and not from 0. They count that from 0. Every time they count from 0. Okay, next slide. Next slide. There is simple reasoning helped us to see that defining membership with respect to a value of reference would solve the problem. There are following the principles of exclusion and contradiction by fuzzy sets. Once again, the Goaltore principle of one not being able to judge anything beyond one's knowledge came into picture. And we decided once again, this time without any fuss, to publish our findings locally. It means this is regarding the definition of complement in the same journal. Okay, next. I don't think much is left. Next slide, please. I think time is up already. So without thinking that membership value and membership function need not always be the same, a definition of complementation was forwarded, which has led to invalidity of the principles of exclusion and contradiction. Instead of thinking that a rather unusual kind of situation has been arrived at, the researchers in fuzziness just followed the leader blindly. Next slide, please. Acceptance of our views notwithstanding, what we have defined is a truth concern. Even if researchers come forward to accept what we have just described, they need to understand that it might actually be very difficult for them to make most of the examiners see reason. Galileo was punished for supporting the Copernican views. Next slide, maybe the last slide, I'm not sure. So those who are interested, they can please go through this. This particular journal is no longer published, but it is available in ResearchGate, fortunately. And this is also available. This is for vectors. The idea was on for general. I named it actually, theory of fuzzy sets, beliefs and realities, theory of fuzzy sets, etc. Next, please. Next. So this is the addendum about certain articles. The slides are which in the screen, and if anyone is interested, it can be taken. These three are simply addendum. Okay, go ahead. And these are the articles which were published in 1999 in the Journal of Assam Science Society. So that I could refer to 1999. Now, come next. I think that's so. Here is the paper itself. It got published in the Pattern Recognition Letters, which one research student of mine. in 2008, and for finding the calendar-based periodic pattern, we used the concept of superimposition, etc. And they accepted it. And then many people have done, there are PhDs on that. Anyway, next, please. I think that is the last. So please allow me to conclude now with the following comments. In my eyes, actually, if you search for it on the web, you will find it in the research kit. I've already written. Mathematics is the best kind of poetry. If one can find a rhythm in it, I feel mathematics must follow logic, and it should never be the other way around. Next, I think they're last. Okay. Thank you. Thank you for listening. I suppose people have not got bored. Yes, Nasreen?
No, sir. They actually not get bored because the presentation was very excellent. And you have discussed about your new invention, new era. Thank
Okay.
you, sir. Sir, actually, we have some questions from our colleagues. May I ask a question, sir?
Yes.
How can integrate, sir? How can we integrate the rough set theory and fuzzy set theory in a single model?
No, in my eyes, this rough set theory kind of things, these are absolutely peculiar. As I said, logic should be followed by mathematics, please. First you do some mathematics, then try to impose some logic. I do not like it. Things like soft set, etc., etc. People have used. I'm not actually, saying that they are doing all sorts of silly things, but I'm not really. I have never shown any interest in studying what soft set, intuitionistic sets, etc. are, because the basic definition, in my eyes, was wrong after all. So why should I go for the extensions? That's why, regarding soft set, I have seen. There is one Tridip. I just remember the first name. They have used my findings in defining soft sets and all. They have defined. So Tridip Neuk. He's from Assam. I have never seen him. And then they have published quite a few things, which I found that they are very peculiar. What was the use of defining a soft set? It was the first thing. Anyway, people are doing. And as I said, when it is a matter of just one individual against just everyone, mathematics is not a cult. It is different from politics. Mathematics should follow logic. That's it. It shouldn't be the other way around, please. So I'm sorry, I cannot make any comment on the link between soft sets and fuzzy sets from my perspective. But people have used it. I don't know how. I named the name. This person, his name was Tridip Neuk, and he has actually linked my ideas into his definition of, his generalization towards soft sets. But I have not gone through that. Yes, next. Any more question, please? Yes, go ahead.
Yes, sir. One more question. Can a fuzzy membership be true and false at the same time? Can a fuzzy membership be
can a fuzzy membership
at the same time?
No. Can a fuzzy membership function?
Membership. Actually, he asked that question. Can a fuzzy membership be true and false at the same time?
So that is, I have not understood your question. Fuzzy membership function and what? What was the next word? Maybe it is echoing, so I'm unable to listen properly.
Maybe it is fuzzy membership function, I think.
Issue, fuzzy membership issue means? I'm unable to listen to that word. Please spell out the word fuzzy membership.
Function, I think.
Okay, fuzzy membership function. Yes, fuzzy membership function. Now, can a fuzzy membership function? And next part of the question?
Be true
Can
and false at the same time.
No. No, that's what I had been telling. That's what I had been telling. They have gone for a particular kind of logic where, suppose capital A is a fuzzy set, and A complement, suppose AC is its complement. Then, according to them, according to their original definition, which was used in, and fuzzy logic, they have gone to use it in even washing machines. My good God. So they say that A intersection A complement is not equal to phi. If you make a statement, you call it capital A, then its complement means, suppose this glass is full of water, and that means say up to 3/4. That is a statement. So its complement will be this glass is full, say up to the level of 1/4. And both together it is equal to 1. But that 1/4 you have to count from the level 3/4, not from 0 level again, because that would make that the complement is included in the original self, which is a pure kind of nonsense. And therefore, extremely sorry. For fuzzy logic, I have no respect. I have no respect. Therefore, what should I say? I don't have any comment actually, because they have used it in such a peculiar way. They have formed a cult of their own actually. They don't believe in what others say. Well, I mean, had I been in USA or maybe in some such big university, big place, maybe my finding would have been, yeah. But now they remain. Yes, there are some supporters I have seen, even in Russia and in Europe. There are some people who have actually cited this article, this theory of fuzzy sets, beliefs, and realities. Now that the journal is no longer available on the web, so people have also lost interest because the journal got defunct a few years back. The article was published in 2010, etc. I'm thinking of reviving it now after I am retired. And one more point, actually, I would like to add. I have said there, it is not exactly as an answer of a question. You see, suppose there is a statistical random variable. Suppose you take, say, rainfall. Okay, today it may rain, tomorrow it may not rain. So you can count. That's a statistical thing. So the question of randomness comes into picture, the question of probability will come into picture. It means statistical analysis is sufficient to do that. But there are certain variables which are expressed in terms of interval. They come automatically. You take the question of temperature. Say at 3 a.m. in the morning, it is the coolest time of the day, therefore the minimum temperature can be seen at that particular time. Say by 3 p.m. the maximum temperature will be seen. So ultimately, temperature in the city of Kolkata, that always is a continuous thing and within an interval. So A1, B1 on the first day, A2, B2 on the second day, A3, B3 on the third day, and so on. You superimpose them and see what comes. You get a fuzzy number. I have seen that. Say stock in the stock market, say price of a particular commodity. Okay, starts say somewhere and ends say by 5 p.m. somewhere, but then there will be a minimum and there will be a maximum. You take the minimum and maximum for the last 15 days. Don't go more than that because ultimately the patterns change. So you will get a fuzzy number. I have seen that. When there's an earthquake, and then in a machine, what is called, that shows actually that there's an earthquake going on. It will be drawing a picture automatically, a curve. Then you just superimpose them. You will get a fuzzy number. So such kind of variables are there where a variable lies between one value and another, A1, B1, A2, B2 kind of things. There you apply fuzziness because two laws of probability automatically comes into picture. I have seen that in stock market, in studying, say, earthquake structures, and such things. And as far as the axioms are concerned, our Professor Asario is there. and she's from theory of graphs. So in theory of graphs, actually, what I have seen is there are too many results which are true, but the proofs are not there. Therefore, they are simply lying as certain results only, but they are true. It's very difficult to prove those results. So you just assume and then go ahead. You cannot just wait till the proof arrives. So here also, people should have seen about the physical significance. So you see, temperature as a whole, temperature every day, not at a particular time. The daily temperature in the city of Kolkata, for example, in case of the stock market, this is not a field where statistical matters should be applied, statistical analysis. It is under the fuzzy law, and I have done that. I have published also such things, but then the examiners concerned were very kind in this case. Well, I have nothing more to say. If you have any more questions, please go ahead. Because I'm not very sure how my words would have been taken.
So I request Professor Mukti Acharya, ma'am, if you have any question, please ask.
No, I don't have any questions. I will just give my thoughts and I will share my thoughts with him. Naturally, I work in graph theory and science. You have sets, then came fuzzy sets, then logic, then fuzzy logic. Okay. Now we have graph theory. Now there is a fuzzy graph theory. Somehow nothing goes into my head regarding fuzzy graph theory. So
that's what I mean, madam, by physical significance. If you see, see, I mean, obviously you seem to be a person from say pure mathematics. There may be viewers and there may be listeners from pure mathematics right now. Nasrin is from discrete mathematics. I know that. Now the thing is, how do the axioms arrive? The axioms just do not fall from the blue. People once upon a time observed that if I say 2 plus 5 equal to 7, that means addition of two integers is again an integer. Then again, all right, all such things like 2 plus 5 equal to 5 plus 2, kind of things. For every 2, there is a minus 2. As a 2 plus minus 2 is equal to 0 and all that. So they have observed these 4 things for all kinds of integers, and then they have simply written in symbols, like if, say, there is a set, and which refers to an operation called addition. If we just write, say, a plus b also, should be in a particular set kind of thing. So these 4 things, these 4 postulates came automatically. They do not fall from the blue because they are simply there. You have to only see that, yes, these are the true things. This is the truth. So in your graph theory also, I have seen one cannot wait for the proof of a result, but the result is true, and therefore just go ahead citing that also. That was not given to me. That particular facility was not given to me. Very sorry, actually. Whole life I have been doing such things only.
Right. Sometimes the ideas will not be accepted by others because they don't want somebody should go above them. That's the mostly which is happening in the world. I don't say society, I will say in the world, even in academic fields. Just I want to know your opinion. See, the engineering colleges, in the beginning, they have computer science.
All right.
Later on, everybody started thinking, let us have more students in our college. So, computer science, they coined information technology, and they called software computing. So, BTech in computer science, BTech in information technology, and BTech in soft computing. If we take up their syllabus and compare, they're not much different.
They are not much different. Actually, as a matter of fact, and based on this, principles of fuzziness forwarded by Lotfi Zadeh, and then again generalized by others, as I said, without much thinking, so many softwares have been made that I just could not fight against all these things. So, if suppose there is a course on BTech on soft computing, it is all right because as long as you get some results, it might look all right. Even in big data analysis, I don't see that there is enough of mathematics there. Big data analysis is actually heuristic, but then people are using what can be said and done. Yesterday, in a discussion, it came out. You were there. I have seen you were there in that particular this Newton-Raphson method. And then yes, and someone asked actually that what is the best, and then the answer was the Newton-Raphson algorithm was the best because it is at least better than the this so-called the method of false positions, regular falsi. Okay, that answer was acceptable. But when were these things discovered? Long back when there was no computer.
Yeah.
This Newton-Raphson method was discovered, was found out long back when we could not even imagine that there can be a computer kind of a thing. So if you go back to those days, means yesterday's answer was acceptable. I agree. But then if you go back to the old days when Newton-Raphson algorithm came into being, you see, Newton-Raphson algorithm is fast enough. That is true. But nowadays there are computers available for. So if the NR algorithm is of, second order convergence, and the this regular falsi is of first order convergence. So obviously it is a slow thing as far as the computational matters are concerned. But nowadays so fast computers are available. Just I don't see any difference between these two. What is the difference between the first order difference and second order difference? It is so fast. When I was a student, in IIT Kharagpur, computer that was made available to students was simply an IBM 1620 with 64K memories, 64K bytes, only 64K. Now, my cell phone or anybody's cell phone is not K, not kilobytes. It talks about GB. All talks about GB. So we are carrying a computer in our pocket every time. So the things have changed. So although the answer was correct, what I mean is basically the method of regular falsi was better. It is better. Although it is very slow, but it was better to do. You don't have to differentiate anything. You don't have to see that this differentiation ultimately doesn't become equal to zero at some points and so on. But then, well, now things are different. Times have become changed. So some things are simply classical, like say Newton's calculus. You cannot change it. But in this next calculus, this discrete thing, well, things are changing. Like a typewriter was there once upon a time. Now it is simply gone. This, Telegram kind of thing was there. Now SMS has come up. Now WhatsApp has come up, and who cares for asking a question? What exactly was defined by a telegram? So things have changed, madam.
Yes.
Things have changed. Things have changed.
I agree. Thank you very much. It's a nice talk. Awareness about the literature in your field.
Okay, if you are satisfied, I observed that you were hearing, you were listening. So
No,
I was
I
a bit confused.
I will try to be live for all the.
Okay. Okay. Thank you very much.
Thank you, sir.
Okay, Nasrin.
We'll call you again.
Okay.
Now we are coming to the end of the session. Now I would request Dr. Partho Agosti, the organizing secretary of today's national webinar on recent advances in mathematical sciences, to give vote of thanks and end the session. Partho sir, please.
Yes. Nasrin, am I audible?
Yes, you are.
Nasrin? Okay. Good afternoon, everyone. It's an honor for me to express my gratitude to everyone present here on this day. I, Dr. Partho Agosti, on behalf of SBSS Mahavidyalaya and the entire organizing team, extend my hearty vote of thanks to all the speakers for gracing their important work and sharing with us their findings and opinions. We are grateful to Professor Mukti Acharya ma'am, visiting research mentor, Vice University, Bangalore, for expressing his idea on the topic degree splitting and eccentricity splitting of graphs. She explained the results on characterization of degree splitting graph of a graph and the results on chromatic number of eccentricity splitting graph of a graph. Ma'am, thank you for making this webinar interesting and fruitful. I must mention our deep sense of appreciation to Professor Madhu Mangal Pal, Professor Vidyasagar University, West Bengal, for his explanation on the topic Newton-Raphson method. He described its variety and its beauty. Sir, your talks always motivate us. We are really enlightened with your knowledge. Thank you, sir. Further, we are grateful to Dr. R. Sundareswaran, sir, Assistant Professor, SSN College of Engineering, Chennai, for demonstrating his work on the topic Influence Integrity in Graphs. He discussed its application in brain network system. I really must express my admiration for your speech. Thank you very much, sir. I also wish to express my sincere thanks to Dr. Anita Pal, ma'am, Associate Professor, NIT Durgapur, West Bengal, for giving an excellent coverage on the topic application of minimum spanning tree in water supply management. Ma'am, as usual, your speech brought new insights from current research. I am very grateful to Dr. Sheikh Mohammad Abu Noim, sir, Assistant Professor, Alia University, West Bengal, for his analysis on the topic Laplacian eigenvalues and Kirchhoff index of some graphs. He described about Laplacian matrix, its eigenvalue, Kirchhoff index, and its bounds. Sir, thank you very much for such a wonderful and informative session. I would further extend a hearty thanks to Professor Hemanta Barua, sir, Emeritus Professor, Royal Global University, Guwahati, and former Vice Chancellor, Bodoland University, Assam, for giving an excellent outline on the topic mathematics of partial presence. Sir pointed out a new idea, named it as mathematics of partial presence, which is different from fuzzy set theory. Thank you, sir. We enjoy a lot from your session. I take this opportunity to specially express my deep regards and gratitude to Sri Shikanto Mahato, President, SBSS Mahavidyalaya, for always encouraging us and providing opportunities to organizing such events. I extend my thanks to our beloved Principal, sir, Dr. Montu Kumar Das, for his unfaltering support and confidence in us. Well, dear audience, an event like this cannot happen overnight. The wheels start rolling weeks ago. It requires teachers' planning and a bird's eye for details. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues, Dr. Nasrin Khan and Mrs. Moitriti. My deep sense of appreciation to the organizing team for all their efforts. Last but not the least, this event would not have been successful without the participation of wonderful audience. Thank you all, hoping the same response from your side for future webinar. We as a human being do best in what situation. This disease made us all to learn digital and go digital. Stay home, be safe, take care, and here I conclude this session. Thank you very much. Have a wonderful day ahead. Thank you.
Thank you. So,
Thank you.
okay.
Thank you, sir.
Now that the meeting is over, actually, to Professor Acharya, I would just like to say one thing. You see, Professor Acharya, because you raised the question regarding computer science,